Hello. Hi. We're gonna start in a few minutes. I think today we're gonna have. We're gonna start in a few minutes. Oh dear. Okay. Let me just turn my phone into silence mode. Hi everyone. Welcome to the stream. So just a quick announcement. Typically on Tuesday we'll have a measure series stream this evening, but tonight I can't do it. Here. Hi Ekan. Thank you very much for joining the stream. Are you KC3 in Discord? Hi everyone. So yeah, um, tonight there won't be any measure series stream because um, I have other things tonight. So the measure series stream this week is rescheduled to Thursday. Okay. So on Thursday, it's measure series. On Friday, there's Friday evening. That's the Oh, great. Awesome. Great to see you. Hi, Vernon. Thank you for joining the stream. And on Friday, it's going to be information theory, the elements of information theory, in particular, the notion of mutual information and KL divergence. Um, Very important concept in statistics, but I never learned it from an information theory perspective. So, gonna be very exciting. And on Saturday, well, it seems like I have activity every day. So Saturday is going to be Leo teaching me some category theory, and it's going to be live on his channel. And because he prefers to announce stream um, a bit closer to the day that actually happens, so right now we don't have a link yet, but I'll post a reminder on Saturday. And actually, on Saturday morning, there's going to be a Leo stream on category theory. On Saturday evening, it's going to be our usual mathematical statistic slash ballistic stream. And on Sunday, because I have this week in particular more church obligation than usual, so there won't be any activity on Sunday. Okay, and there should be also video uploads during the during those course of this week as well. So, yeah, thank you very much once again for joining the stream. And without further ado, let's get started. So, what do we wanted to do in this stream? So, we're going to introduce rotations, and it's going to be a fairly elementary introduction to rotation because rotation is such a fascinating subject that you can discuss it at so many different levels. Okay, and you can it's our approach. Okay, our material today is going to be mostly computational, quote unquote computational. It's going to be more intuitive. There's going to be a lot of diagrams and whatnot because, as the title suggests, this is for game engine and graphics engine development. Right? So it is more um, a recipe. But I do wish to motivate everything and derive everything from scratch. So these aren't just black boxes. Okay, and of course, when you get into higher levels of mathematics, rotation is a fascinating subject because it is connected to topology and geometry, and also algebra, abstract algebra. So, absolutely fantastic, fascinating stuff, and it's got a lot of history to it. Okay, so but today we would just wish to get to the fundamentals of it, so you can actually work with rotations, and in particular 3D rotations. And a prerequisite for our material today is a familiarity, passing familiarity with vectors and matrices. Okay, you don't necessarily need extensive backgrounds in linear algebra, but you do need to at least see things like vector dot product, cross product, matrix vector multiplications, matrix multiplication, that sort of thing. Okay, but don't worry, we will review them as we go along. Okay, so before talking about 3D rotation, it's instructive to look at 2D rotations first. Okay, 2D rotations. So here we have a diagram that illustrates 2D rotation. So here we have x1, x2 coordinate system. So this is R2, the Euclidean plane. And let's consider a vector. Let's consider a vector, and suppose we wish to rotate this vector by a fixed angle, say theta. Okay, and by convention, if we just say rotate by theta, we mean counterclockwise rotation. Okay, so that's the situation. So the transformation is as follows. So we wish to describe the relationship between the rotated vector and the original vector. Okay, so let's do that. So let's just call the original vector x1, x2. And in the classic linear algebra fashion, we represent vectors as column vectors. Okay, so that's the original vector, and the rotated vector is x prime. So x prime will have coordinates x1 prime, x2 prime. And we just wish to derive a relationship between them. Of course, you need a little bit of a trigonometry to do that. Okay, so this is, this is x vector, and this is x prime vector. Okay. At some point, it's likely that I will be sloppy and drop the vector symbol, and hopefully it's still clear what we mean from the context. Okay. Okay. So perhaps it's easier to work with polar coordinates. Perhaps it's easy, but we'll write our formula in Cartesian coordinates, but the derivation is probably easier in the polar coordinates. That is, the rotation always fixes length. So let's call the distance between the origin, so actually let's just call the length of x vector to be r. Okay, so the length is r for the original vector, and let's call the initial angle. By initial angle we mean by angle. Okay, by an angle of a vector, we mean the angle it makes with the positive x1 direction. So that's the polar coordinate. So r and this angle alpha together forms the polar coordinates of the vector x. And by the way, we assume vector x is non-zero. Okay. We assume that otherwise the angle alpha is undefined. The length is, actually let me just write it as this way. The polar coordinate is polar coordinate is r and alpha. Hide the blue. Thank you very much. And of course, after the transformation, the polar coordinate becomes r and alpha plus theta, because the length stays constant and the angle just increased by theta. See, so the transformation in polar coordinates is very simple, and we just wish to convert everything back to Cartesian. So using simple trigonometry, we know by trigonometry, we know x1 is r cosine of alpha, x2 is r sine of alpha. Okay, and x1 prime is r cosine alpha plus theta, and x2 prime is r times sine of alpha plus theta. Okay, this is clear from the diagram. Draw your little right triangle, if you will. So, and now we're just going to use the trig identities for cosine of alpha plus theta and sine of alpha plus theta. So these are well-known trig identities called the addition theorems or addition formulas. Okay, x1 prime is r cosine of alpha plus theta is cosine of alpha cosine of theta minus sine of alpha sine of theta. Okay, that's x1 prime. x2 prime also can be expanded similarly, so you get r times sine of alpha cosine of theta plus cosine of alpha times sine of theta. So we wish to convert everything back to the original Cartesian coordinate x1, x2. And we can do so easily because r times cosine of alpha is x1. You see r times cosine of alpha, that's x1. So you just get cosine of theta times x1 minus sine of theta times r sine of alpha, which is x2. This is x2, all right? So then do the same for the second equation. And we see, and by the way, I just wanted to keep things organized. I'm going to put the second term at the front because r cosine alpha gives you an x1. We wish to put every x1 term ahead of x2 term. Okay, it's just an aesthetic choice, which will make things convenient. Okay, sine of theta times x1. That's sine of theta times r cosine alpha. Okay. And then plus cosine of theta times x2. All right, so we have our transformation formula. So let's just put everything together. So x1 prime equals cosine of theta x1 minus sine of theta x2. And x2 prime is sine of theta x1 plus cosine of theta x2. So it's pretty neat. And of course, we can write it in the matrix form. So the right-hand side is a matrix vector multiplication. We write it this way. So x1 prime, x2 prime. First of all, this is equal to the vector cosine of theta x1 minus sine of theta x2, sine of theta x1 plus cosine of theta x2. Of course, these two vectors are equal, and the vector on the right-hand side can be expressed as a matrix vector multiplication as follows. Cosine of theta minus sine of theta, sine of theta, cosine of theta. Okay, and then times the vector x1, x2. So we're going to call this matrix. Okay, so just in case matrix multiplication is a little bit rusty, so matrix multiplication works this way. You take starting from the first row, you take the first element and multiply with the first element in the column. Okay, so cosine theta times x1, and then you proceed to the second element in the first row, minus sine theta, and then multiply that by the second element in the column vector x2. Right? So this way, you get cosine theta times x1 minus sine theta times x2. And you repeat the same procedure for the second row. Sine of theta times x1 plus cosine of theta times x2. Okay. I suspect this was originally discovered to simply save some writing. Because as you can see, this way you don't need to write x1, x2 twice. You just need to write it once. Okay. And keeping all the coefficients in this table manner, tabulated manner, loses no information. So that's the matrix form of this transformation. So, and of course, this is important object. As we can see, this matrix completely encodes all the coefficients in this transformation. So let's define the rotation matrix, R theta. Okay, sometimes it's written as R of theta. Okay. I just tend to use the subscript symbol. Define R theta equals cosine of theta minus sine of theta, sine of theta, cosine of theta, as the 2x2 rotation matrix, or the 2D rotation matrix. Okay. So the key characteristic of this rotation matrix property. The key characteristic of this rotation matrix is that, as you can see, each column is a unit vector. The columns of, and in fact rows as well, and rows. But typically we only need column vectors for the sake of the topic of this video. The columns and rows of R theta, properties plural, of the columns and rows of R thetas are so-called orthonormal vectors in R2. Okay, what do we mean by that? It means the columns, they all have length of 1. And by the way, we use the notation double vertical bar in place of single vertical. A single vertical bar represents absolute value. We use double bar to distinguish it from the absolute value to indicate the argument is a vector. But often we get lazy and just write the single bar as well for the length. Okay, this is the length. The length is the square root of cosine square of theta plus sine square of theta. Of course, this is just 1. And of course, the second column, you can verify that the second column also has length 1. Okay, and it is also true that the columns are orthogonal. So to verify that, you just need to take the dot product between the two columns. So here's a quick review of the dot product. To take the dot product, you would multiply, and by the way, we'll do a more systematic review of dot product a bit shortly when we introduce 3D vectors. Okay, so but basically what you do is you would multiply the respective entries and sum up the individual product. So you cosine theta minus times minus sine of theta plus sine of theta times cosine of theta, which equals 0. And dot product equals 0 means orthogonality. Means the two vectors are orthogonal. And here we have a picture of these vectors. So there we go. And they actually have very nice geometric interpretation. So on the original plane, x1, x2, first of all, we have the standard bases, so-called standard bases. The standard bases are simply unit vectors in the positive direction of the coordinate axes. So along the axis x1, we have the standard basis vector e1 equals 1, 0. It just means that x1 equals 0 and x2 equals, x1 equals 1 and x2 equals 0. That's e1. And the second basis vector e2 is 0, 1. Okay, sometimes we write, the notation e1 equals so-called I. Okay. Oh, I already starting to get lazy because I dropped the vector symbol. Okay, so let me put that. Okay, but as you can see, it's not much is lost, right? If I don't write the vector symbol on top, you can say, oh, e1 is 1, 0. That's a vector. It's usually noted that orthogonal is a fancy word for perpendicular. I know, right? It means the same thing. Orthogonal means perpendicular. Okay, anyway, there's a funny remark in Sheldon Axler's book, Linear Algebra Done Right, on the word orthogonal being used in everyday life and causes a little bit of a confusion. So in everyday life, it seems to me that orthogonal also means irrelevant. Okay, so a fact is irrelevant to another subject. You can say orthogonal instead of irrelevant. It's a fancy word for that as well. Okay, anyway, that's according to Sheldon Axler. I'm not a native English speaker, so I'm not sure if that's actually the case. So I just tend to use the word irrelevant in order to avoid confusions. Anyway, so what is going on here? So we have these two basis vectors along the directions of x1 axis, x2 axis. The columns of r theta are simply the result of applying the rotation transformation to these basis vectors. Let me use a different color. So if you rotate e1, and now we have a notation now, it's this r theta times e1. Right? Because after you define the rotation matrix, the rotation formula now can be compactly written as x prime equals r theta times x. Right here, x prime vector is r theta times x. So that's the formula. Okay, so here, if we wish to apply the rotation to e1, you simply get the red vector. I found no meaning. Okay, yeah, go check out the Axler's book on linear algebra. I will not do it here because that's a distraction. Because we have a lot of stuff to talk about. It's quite funny. In Axler's text, Linear Algebra Done Right, the chapter on inner product spaces. Anyway, so this is r theta times e1. This is r theta times e1, and of course the angle is theta. And of course, from trigonometry, this is clearly just cosine of theta, sine of theta, because the length is 1. Okay, and you can do the same thing for E2. Okay, so this is r theta E2. R theta E2 will have coordinates minus sine of theta, because you can see this is theta, right? This is theta. So the x-coordinate would be is on the negative part of the x1 axis, so it's a minus sine of theta. So the triangles to clearly see what's going on, and let's put a circle as well to indicate the constancy of length. So all four vectors have their tips on the same circle, the unit circle on the two-dimensional plane. Right? Okay, so minus sine theta, that's the first coordinate of r theta times e2, and the second coordinate, of course, is cosine of theta. So r theta is what? R theta can be written this way. So therefore, r theta from this diagram, actually, you know what? Let me put the thing here. This is a property. I mean, this is a general property for linear transformation, but I think here it's worth mentioning because this is a nice visualization. What I'm about to write is the matrix R theta is made up of columns in this way. So the columns are R theta applies to E1. That's the first column. So these are just two vertical dashes on top to indicate this is a column. Okay. R theta applied to E1, R theta applied to E2. Okay, so this is the first property. I'll put a 1 here. This is the first property, this is the second property. So you can see what the columns of R theta represent. Okay. But I will I will avoid using the notation ijk for the standard basis vector, because later on we will use what's that? Complex numbers. So we'll use I, and this may cause confusion. So I'm just going to stick to the notation E1, E2. Okay, so there's that. Okay, so lastly, the determinant of R theta. The determinant of R theta is always 1. And it's quick to verify. The determinant of R theta, you just use the determinant for the matrix, 2 by 2 matrix. So the determinant of cosine theta minus sine theta, sine theta, cosine of theta is, once again, you multiply the diagonal and then you subtract the product. So this is cosine theta times cosine theta minus negative sine theta quantity times sine of theta. And this is, of course, cosine squared plus sine squared, which gives you 1. What this means is that rotation preserves the orientation, as well as preserves the orientation. In order for a transformation to preserve orientation, for a linear transformation to preserve its orientation, you simply need the determinant to be positive. But here, the extra fact that the determinant equals 1 tells us rotation does not distort volume. So verbally, this equation means rotation preserves orientation. So that is to say, for example, in the basis E1, E2. So to get E1 into E2, you need to rotate E1 90-degree counterclockwise to get to E2. Right? So that's the relationship between E1 and E2. And after the transformation, say the vectors E1 becomes R theta E1 and the vector E2 becomes R theta E2, the relation between R theta E1 and R theta E2 is the same. Orientation is preserved. The rotation preserves orientation and volume. Okay. Once again, this is a basic fact from linear algebra. Determinant is Determinant measures the determinant is the volume distortion factor of a linear transformation. Okay, so and speaking of which, I should probably put the zero property as r theta is a linear transformation. 2D is a 2D rotation is a linear transformation. I should probably put that first. Okay, I'll do the rearranging in a bit, but let me just put it as property 0. Okay, I'll do the shuffling after. R theta is a linear transformation. And there are two ways to see this. The first one is algebraic. Is a linear any linear transformation from R2 to R2 would have the form algebraically would have this following form. Okay, any 2D any linear transformation in 2D has the following form. Namely, x1 prime, x2 prime are linear functions of the old coordinates. So x1 prime is a11 x1 plus a12 x2, and a2 x2 prime is a21 x1 plus a22 x2, where aij's are independent of x1 x2. Okay. So here, of course, this is equivalent to the matrix form, namely x prime vector equals matrix A times vector x, where A is a 2 by 2 matrix whose entries are aij's. I find the force meaning under orthogonal very different, unrelated. Yes, very different or unrelated, sharply divergent. Yes, that's the real world meaning I was talking about. But perhaps it's so rarely used that if you drop this word in a non-mathematical context, it's more likely to cause confusion rather than you have to probably explain the word later. So, which is inefficient. Okay, anyway, so here you have this matrix A. So any linear transformation in 2D has this following form. And of course, here we have A11 being cosine theta, A12 being minus sine theta, A21 is sine of theta, A22 is cosine of theta. So these are all independent of x1, x2. So this fits this definition. So this is algebraically speaking. But in a more coordinate independent way, okay, because in geometry we like to define things independent of coordinates. A linear transformation is one that has the property geometrically, or you can call it intrinsically, r theta of x plus y, vector x plus vector y, equals r theta of x plus r theta of y. So on the left hand side we have a vector addition, x vector plus y vector, and then you rotate the sum vector. And on the right, you do the rotation for each individual vectors first, and then add the rotation results. So that's the first property, and the second property has to do with scalar multiplication. If you multiply the vector x by a constant, say c, is the same as c times r theta x. Okay, so the first property is a distributive law. But the second, just say you can pull out the constant. And both properties can be verified geometrically. So linearity, these two together are called linearity. And in fact, starting from this definition of linearity, you can actually derive the general form of linear transformation in the way we just written down. And that's a task, standard task in linear algebra course, which I will not do here, just to review. But here, I'm just going to verify these two properties geometrically. So you have, say, two vectors x1, x and y. So this is x, and this is y. There's also a nice review of vector addition. So this is y, this is x, and their sum is given by the parallelogram law. Okay, so x plus y is this diagonal here. Okay, and then you can just rotate this whole diagram. Actually, can I do that in decimals? Or not decimals, but in OneNote. That would be awesome. Yeah. Okay, you can just rotate the whole thing by the same angle, okay, by theta, okay, and you can see that the corresponding vectors also gets rotated by the same angle, x and y and their rotated counterpart. Okay, so there you go. You have this diagram here. So let me just change the color of that to denote the rotated version. Can I do that? Change color. Okay, change that to. Okay, so yeah. This is what I wanted. Okay, so I'm gonna label the results. So you see r of x, r theta of x. Okay, and here's the rotation angle, for example. So it goes from here to here. This is the angle theta, r theta of x. The diagonal is r theta x plus y. And this is y. So that's the first property. Oh, sorry, not r, but not y, but r theta y. Okay, so that's the first property. If you rotate the sum, you get this, and the sum, and if you rotate the sum, you get r theta times x plus y quantity, and it is equal to the sum of the outcomes of individual rotations. The rotations of individual vectors. So there's that. And the second property is even easier to visualize. So you have just one vector x, and then you scale it. So this is x. This is cx. Okay, and you apply the rotation. You can clearly see this is the rotated version of x, so that's r theta x. And this is a scaled version after rotation. So this is r theta x times c. And of course, this is the same as r of r times cx. It's the same. Okay. So r theta is a linear transformation, and this should be zero, property zero. Okay, this should be property zero. Okay, so these are properties we wish to generalize into higher dimensions. So that's pretty much for the matrix formalism of 2D rotation. So if there's anything unclear, please raise it right away, okay, in chat. I know I tend, in this video, in this stream, I probably go through things a little bit slower than, say, in other streams. but for a good reason, because I really wanted to start from the very beginning. I haven't do this stuff for a long time, and I don't want to make any mistakes, so I want to see how everything is derived. Okay, so that's the first formalism, but now let's take a look at the second one. It's called complex number formalism. So that's actually very interesting. That's actually very interesting. So that's actually the first breakthrough in the study of complex numbers. So complex number was, you guys probably know, initially viewed with great suspicion. So what on earth is the square root of a minus 1, right? So what's that? A complex number turns out to be a great way to describe 2D rotation. And let's see how that works. So recall, the complex number multiplication is defined as follows. So if you have, say, a plus ib times c plus id, and we just expand this product in the usual way and use the rule I squared equals minus 1. Of course, I cannot be a real number. This does not exist. But let's just assume that I is an abstract symbol that has this property. And a plus ib, c plus id can be expanded in the usual way. The usual way we do algebra. Okay? By the expansion, you get ac plus a times c plus aid. Okay, and then ib times c, and ibid. Okay, and we assume that multiplications are commutative. You can commutative, associative, all those good stuff still hold. Okay, we assume that, and you can use the last term, rewrite the last term as minus BD. So you get AC minus BD plus, and then factor out the I, you get I times AD plus BC. Okay, so we're assuming all the usual rules of algebraic manipulation with the additional rule that I squared equals minus 1. So that's the complex number multiplication. This is defined this way. Okay, so I'm not saying this is how it is proved. Okay, the formula is not proved, but rather this is a definition. This is a definition of complex multiplication, and we're just going to investigate the consequence of this definition. So as you can see, the right-hand side looks a lot similar to the addition theorem of the trigonometry that we just used. This is very similar. So this is where actually the complex number becomes handy when it comes to rotation. So, okay, a point on the complex plane, this is C. Okay, this is C. So you have the real axes and the imaginary axes. So, yeah, this is, for example, a plus ib means a vector on the complex plane. Okay, and we can, of course, rewrite the vector in the polar coordinates as well. Assume vectors. Assume non-zero vectors or complex numbers. Let's write a plus ib. Let's write a plus ib as r cosine of theta, actually cosine of alpha, times I r sine of alpha. So that is to say, we let the length of the vector to be r and the polar angle to be alpha. Okay, same idea as earlier. And we write c plus id as, say, rho times cosine of theta plus I rho cosine of sine of theta. So what does the formula above tells us? It says R cosine of alpha plus I sine of alpha rho cosine of theta. There's going to be some overlap with my video on complex numbers. So if you've seen that and know where this is going, I apologize. Okay, this is not to create redundant content, but simply to for the sake of making the presentation self-contained. Okay, and AC minus BD is what? AC minus BD, that would be R rho cosine alpha cosine theta minus BD, that would be minus R, this is A times C, B minus B times D, so you get R rho sine of alpha sine of theta. Okay, and then plus I times AD plus BC, so A times D, which is R rho cosine sine of theta. I just write it this way: sine of theta cosine of alpha, and plus BD, right? Plus BD, P plus BD, so plus R rho sine of alpha cosine of theta. Okay, and you can simplify the right-hand side using the trig identity, so it will be R rho times cosine of alpha plus theta plus I R rho sine of alpha plus theta. It's the same business we did earlier. Okay, so this gives us an interpretation of complex multiplication. It's basically rotation. You add the angles, and then you multiply the length of the complex numbers, or the modulus. Interpretation. Multiplying two complex numbers is equivalent to multiply the length and add the angles. That's quite nice. That's quite nice. So let's draw the picture here. Because a complex number are usually denoted using letters such as Z and W. Okay, so this is Z and this is W. Okay, so let's say Z has angle alpha, W has angle theta. The product Z times W would have angle theta plus alpha. So this is Z times W, and its length is the length or the absolute value of Z times the absolute value of W, or complex modulus, and the new angle is theta plus alpha. But of course, adding angle is rotation. So multiplying complex number is also known as scale rotation, because rotation on its own does not change the length. Here, general complex multiplication might also affect the length. So adding angle is simply rotation. But let's just specialize to this case where R and rho, the two complex numbers, all have length 1. Special case. So if you have R equals rho equals 1, what do we get? What's the formula above look like? So we get cosine of alpha plus I sine of theta, sine of alpha, and then you get cosine theta plus I sine of theta. Okay, the left hand side, because we set r in rho equals 1. On the right hand side, you get cosine of alpha plus theta plus I sine of alpha plus theta. So we have the formula that looks like this. And we can write it in a more compact way. So if we just define a function, say f of t. F of t, the function f of t is defined as cosine of t plus I sine of t, where t is just a real number. This reads, the multiplication formula now reads f of alpha times f of theta equals f of alpha plus theta. Think about what this looks like. This is a functional equation. So I'm struggling with the basic topics. It takes me an hour or two just to understand simple concepts like frequency distribution. You mean Fourier transform? Frequency distribution. Does this mean I'm too slow for this subject? No, not at all. Okay, I'm not just saying this in a standard positivity way. Okay, Sunday. So I assume you're talking about the frequency distribution in Fourier analysis, that sort of thing. This is a highly non-trivial content. Okay, not content. I'm doing YouTube for too long. Everything I just call it content. This is a highly non-trivial concept. Things like frequency distribution is highly non-trivial. Of course, you can take it as a black box and just operate the formulas without much understanding going on. But if you want us to say, okay, I want to understand what this means, then of course it takes well over an hour. It can take you a whole day or a whole week to get through statistic construction, univariate by construction, univariate bivariate frequency distribution. I know univariate distribution, bivariate distribution, and what do you mean by construction? Is that a measure theoretic thing? Constructing a distribution? You have to be more specific, okay? So if you can show me a sample like notes or text, because right now I don't know what you're talking about. I'm sorry, but you can also put it in a Discord server. Okay, so and it actually that's not even the point, because whatever you learn in math is likely the result of intellectual labors that span decades, if not centuries. So these notions, these outcomes are not something that is. These are not easy victories, okay, in the course of human history. And even giants struggled with, well, complex numbers. A lot of famous mathematicians, including Euler himself, did not believe these things actually existed. Okay, they thought it as convenient mathematical fictions, which is, for practical purposes, is not totally inadequate. Okay, it can be adequate, but the understanding of mathematical objects, such as complex numbers, such as things like frequency distribution, which I still have no idea what that exactly means, are not easy victories. It's okay to be confused, and it's not because you're stupid. Okay, and it's just a matter of experience, really. What we wish to do, at least that's what I ask about myself, about myself, is I want to reach to a certain stage that I can construct everything from my mind, from scratch. without the aid of a textbook. That does not mean rote memorization. It just means that the concept is so inevitable to me that I don't need an external aid to reach, say, a particular result. Right? So, for example, I don't know about you guys, but from where I grew up, when we first learn things like addition, we have a table. Right? And so on. So, when you first learn this, you do addition with the aid of addition table, and when you become proficient, you simply do not need one anymore. And this is what I aim to achieve to all of math. Okay, of course I will fail miserably at the end, but still it's worth going. You're simply asking what are the steps to construct. Okay, frequency table. Okay, frequency. Okay, great. We'll continue that if you wish. And this is I think that's the basic topic in statistics. So you just collect the. I guess it's like collecting the histogram, collecting data to construct the histogram. If you have a sample and you put your data into bins, and you just count how many occurrence in each interval, right? And then you divide by the total number of observations, you get frequencies. Right? And of course, for the bivariate situation, you would need a table for that. So these are all ranges for individual variables, so you have x and y, and you just count, okay, how many observations where x is in this range and y is in this range, and you put the number here. So this way you get a frequency table for the joint distribution. All right, so enough digression, because we have a lot of things to cover. I'm so sorry, I haven't even get to 3D rotations yet, okay? I might need to do it a second time. Okay, but I don't think we wasted any time, right? So everything is done from first principle, as it should be. All right, so what we're getting at is at this crucial identity for complex multiplication can now be written in this very succinct form, of course, in a special case for unit complex numbers with modulus 1. So you have this relation. What is this? So this looks like one of the Cauchy's functional equation. This is one of the Cauchy's functional equation. So multiplying the function is the same as adding the argument. Multiplying the value of the function is the same as adding the argument. This is one of the Cauchy's functional equation. At least formally. We'll eventually be talking about SO3 and Lie groups. I hope so, but currently I'm still very ignorant about the subject, and to be honest, I'm looking for a nice reference to guide me through this stuff. Eventually, I think I will, because you know what? There's an upcoming stream on information geometry, right? So eventually, we do wish to dive a little bit more deeper into geometry, abstract Lie theory, and that sort of thing. But as we mentioned this at the start of the stream, right? This is, of course, all part of the Lie theory. All part of Lie theory, but here everything is done in a very computational manner, because I mean the stream is for it's a more hands-on approach. Okay, so you can actually calculate things with. But at the same time, I do not want to compromise mathematical rigor. I don't want to just give you the formula and say, okay, this is the rotation formula, apply it to your game engine. Okay, because this way is just external information. It's not knowledge. Information can atrophy. But knowledge is part of your consciousness. So that's why we're starting from the most basic. Okay, so this is in most countries this is high school stuff, except maybe for the matrix part. Okay, but so far we're just using high school algebra. Eventually, I guess, with indefinite timeline. Okay, because this is after all a very one-off stream. The thing is, there's so many interesting areas of math that you feel your time on Earth is so short. Anyway, so this is Cauchy's functional equation, and what is a result regarding that? Well, I'm just going to borrow that result, okay, not applying it because it does not actually quite fit. Here's the theorem. There's a theorem for that, the theorem. Okay, let f be a function from R to R. Okay, assume, okay, assume or if f satisfies the Cauchy's functional equation, let's call it CFE. If f satisfies Cauchy's functional equation and is continuous, then f must have the following form. Then f of x equals e to the kx for some k, for some positive constant k. For some constant k, okay? Here, because f is from real to real, k is a real constant, of course. So this is the theorem. So is cross product important? Both are tremendously important. There's no hierarchy there. As we can see, as we shall see in 3D rotation, we will be using both. Okay, so this is Cauchy's functional equation. It says if the function here is continuous, f is continuous, and it satisfies this equation, it has to take this exponential form. Of course, the converse is trivial. The converse, of course, everybody knows, e to the kx times y is e to the kx times e to the ky. This is just simply the law of exponent. But what's important here is that if f satisfies the functional equation and is continuous, then f must take the exponential form. Okay, here we can't really apply this result because f is complex valued. Okay, in the theorem, s is from R to R. Here, f of t takes a real input and returns a complex output, so it does not quite actually apply. Okay, you can't actually apply the theorem, but inspired by this, okay, not applying the theorem, but inspired by this, we denote f of t, okay, which is cosine of theta, cosine t plus I sine of t, as e to the it, as e to the kt for some constant k. Of course, k cannot be real, because if k is real, since t is real, e to the kt is real. Here f of t is complex. Right? K obviously cannot be real. But what is k? What is k? So, by the way, I just wanted to re-emphasize this again. Okay, we're not applying the theorem. We're just using the form of the conclusion of the theorem and made a conjecture, or made a suggestive notation, in fact, because there's nothing to prove yet. Right? We don't even have a definition of e raised to the complex number. This is simply a notation inspired by this result. After all, here we have f satisfies the Cauchy's functional equation, and f is a continuous function. Even though we have not defined continuity formally, but think about it. F of t, what is f of t? What is f of t? So geometrically, f of t is a point on the unit circle. Geometrically, justification. First of all, f satisfies the Cauchy's functional equation. And f should be continuous. Why should f be continuous? Well, if we think about it geometrically, f of t is a point on the unit circle. And it is obtained by rotating the point 1. Okay, this is not 1, 0 anymore because this is a complex plane. The real number 1 is this point. Okay, not imaginary. This is real. This is imaginary. So by rotating the point 1 by a radian of theta, not theta but t, sorry, you get f of t. This is f of t because it has a real part cosine of t and imaginary part sine of t. So if you varies the argument t by a small amount, f of t in response only changes a small amount. So f of t should be continuous. Right? This is what continuity means. If you change the argument by a small amount, the resulting output of the function also changes by a small amount. So f is indeed continuous. So it makes sense for us to call f of t to be e to the kt, even though this expression is currently meaningless. Okay, and we don't even know what k is. So we need to figure out k. Let's put what is k down here. What is k? So once again, we're going to borrow a fact from regular calculus. That is the calculus of a real valued function of a real variable. What is k? So in inspiration for recall from ordinary calculus, that is for f that takes a real argument into that maps a real argument into a real number, and we have the formula which is e to the kx taking derivative. After taking derivative, and then you set x equals 0, you get what? You get k times e to the kx. It's just the standard result from calculus, right? And you set x equals 0, you get k. So let's assume this hold. Assume this still hold for this f of t. We can recover k. You can simply calculate the derivative, and then set the variable t equals 0. So assume this is still true. Assume this holds for f of t equals cosine of t plus I sine of t, which we write, okay, as a pure notation as e to the kt. Assume this holds for that, we can recover k. So k would be the derivative of e to the kt prime when you set t equals 0. Well, what's e to the kt? Well, e to the kt is just this notation. It's just cosine of t plus I sine of t. And you set t equals 0. So what is cosine of t, I sine of t? Well, it's just the point on the circle. In fact, cosine of t plus I sine of t gives a parametrization of the circle. As t increases, as t varies, cosine of t plus I sine of t trace out the unit circle. So this is a vector valued function, essentially. Cosine of t plus I sine of t, aka ft, is simply a vector valued function. So how do you differentiate a vector valued function? You differentiate individual components. So this is cosine of t prime plus I sine t prime. And then you set t equals 0. Okay, and now we use the derivative formulas, and we get a minus sine of t plus I cosine of t. And you set t equals 0. You just use the special values for the trigonometric functions, and you get simply I. Sine of 0 is 0, cosine of 0 is 1. So is I. K is equal I. So k equals I. So assuming the regular calculus rules still hold for our f of t, we get this formula. So f of t equals cosine of t plus I sine of t equals e to the it. And this is called Euler's formula. And this is called Euler's formula. So now a point on a unit circle can be simply denoted as e to the it. Once again, we cannot stress this fact enough. The whole procedure we just did is not a proof for the Euler's formula, but rather a motivated definition of e to the it. E to the it is now currently defined as cosine theta, cosine t plus I sine t. This is the definition of the symbol e to the it. It's not a proof. This is a definition. Euler's formula definition of e to the it. Of course, I call it the definition because this is true for our exposition. Our exposition in a general, in another way, okay, in another exposition, you can define, you may define e to the z first. You may define for an arbitrary complex number z, what does it mean to say e to the z. You can do that first, and then specialize z to be purely imaginary, call it it, and then you show this formula. That's also okay. In that situation, that'll be a proof. But here, e to the it equals cosine t I sine t is just the definition of e to the it. Okay, I'm late, but I love this topic so much. Yes, it is absolutely beautiful, right? And the depth is incredible, right? Probably high school already teaches this stuff, but you can it's just a gold mine, right? You can be in your PhD and still come back to this and be amazed by it. So this is Euler's formula, and remember, what did we assume here? We assume the regular calculus still hold. We assume this rule holds true. But is that true? Because now we actually have a definition for e to the it. Right? We have a definition of e to the it, so we can actually verify whether e to the it taking derivative is I times e to the it. So now you have the definition, you can now prove e to the it prime equals I times e to the it. Now you can do that. Let's prove it. So on the left-hand side, e to the it, because by definition, it's just a vector valued function. So it's just cosine of t plus I sine of t, taking derivative. We already did that. You just differentiate the individual components, and the result is minus sine t plus I cosine of t. So that's the left-hand side. What's the right-hand side? Well, right-hand side is I times e to the it. So I is just I e to the it is cosine of t plus I sine of t. Use the definition of complex multiplication, you get minus sine t plus I cosine of t. So indeed, everything works out. So that means the derivation we did earlier was okay. And this is a proof, because now you have a definition for e to the it, you can start from that definition and prove its property. So therefore, we're good here. And by the way, there's a geometric interpretation to that as well. Because remember, what is complex multiplication? Complex multiplication is simply scale rotation. Here, I and e to the it both have length 1. Right? I is the north pole of the unit circle. E to the it is an arbitrary point on the unit circle, so they both have length 1. So therefore, there is no scale rotation anymore. It's just a rotation. But what is multiplying I? Well, I has polar angle of just half pi. So I times e to the it is rotation by half pi counterclockwise. Let's draw the picture. Unit circle. The right hand side, I times e to the it. 1 second. Yeah. This is, say this is e to the it. Right, this is I. I times e to the it is rotation by 90 degrees. This is I e to the it. The perpendicular. But what is e to the it prime? Well, e to the it prime we calculate as the vector derivative, the derivative of the vector value function. And of course, the derivative of vector value function is the tangent vector. The vector value function, e to the it, namely cosine t plus I sine t, describes the circle, describes the unit circle. So its derivative is the tangent vector of the unit circle. So that's e to the it prime. That's the velocity. As you can see, e to the it prime and this are the same vector. So here, this identity e to the it prime equals I times e to the it just says the tangent line of a circle is perpendicular to the radius. It just says tangent vector perpendicular to radius vector. Of course, that's true. Okay, so now we understand this formula. Understand this formula, and this is not of course the only way to get to Euler's formula. There are many ways. I will just mention another one. It uses the Taylor expansion, another derivation, aka motivated definition, is as follows. You've probably seen it elsewhere. Is to use a Taylor series. So let's recall a few Taylor series from calculus. So recall you have these formulas. E to the t is the sum of t to the n over n factorial. N goes from 0 to infinity. Sine of t is, sine of t is, it only has even power, so it's -1 to the n times t to the n, 2n plus 1 over 2n plus 1 factorial. N goes from 0 to infinity. And cosine of t is the Taylor series, -1 to the n, t to the 2n over 2n factorial. So in regular calculus, t is real. And in fact, it converges everywhere on the real line for t greater than minus infinity, less than infinity. So t is real here. And once again, let's just make a leap of faith and assume this still holds true for it. So apply this formula inspired by this. By these, let's consider the following. So let's try to calculate e to the it. So e to the it is, assume this still holds, okay, still you get the sum of it to the n over n factorial. So what is I to the n? So what is I to the n? So, well, consider the fact. So let's say this is I to n. Okay, let's make a table here. I n and I to the n.
And it's not hard to see I to the n is periodic. And in fact, there's a nice diagram associated with it, because now we have this little interpretation of complex multiplication. So this is I. I times I is rotation of I by half pi, so it gives -1. That's I squared equals -1. Well, actually, let's start from 0. Okay, I to 0, assume the law of exponents still holds, assume this is 1. Okay. I to the first power, of course, is just I to the second power, that's -1 here. I to the third power, that's -I. And I to the fourth power is 1 again. So you see, this is a periodic. So it comes back to the point 1. So this is I to the 0, I to the 1, I to the 2, and I to the 3. And just keeps switching. Okay, and it just keeps not switching, but progress through the 4 vertices of the circle periodically. Okay, and we keep going. So you have this periodicity, and in particular, the even powers of I are real. 0, 2, 4, and so on. And the odd powers are purely imaginary. So to summarize, you get I to the 2n. I to the 2n is what? I to the 2n is -1 to the n. Yeah, it's so cool. I love the deep bound between geometry and computation. Everything just works. Yeah, it's magical. It's just in complex analysis. I mean, I have a series going on for it. I should probably post the next video. Everything works out so nicely. It feels too good to be true. Okay, and complex analysis. This is just complex algebra. Okay, complex analysis is also super nice. There's no pathological examples there. Okay, almost never. I'm pretty sure if you really look into it, there's some. But basically, there's very little counter examples in complex analysis. Whereas in real analysis, well, pathology is the norm. In real analysis, monsters like nowhere differentiable functions are in fact the norm. So complex analysis is extremely nice, really. So anyway, here we have this pattern. I to the 2n is -1 to the n. I to the 2n plus 1 is just -1 to the n. Is that right? Hold on a second. Yes, that's correct. N goes from it was 0, 1, 2, and so on. Yeah, this is correct. So for 1, n is 0, so you get just positive sign times I. All right, so here we have this pattern, and we can break this series into even and odd indices. Okay, so this might seem like an innocuous transformation. So I'm just saying, so n is either even or odd, right? So let's say n even it to the n, and then we're going to write n equals 2k and whatnot. Okay, n factorial plus the sum n odd. I'm just going to make a little comment shortly. So it seems like a rather innocent operation, right? You can just break the sum into 2 components. But what we're actually doing here is a reordering, is a rearrangement in the series. This is a rearrangement in the series, this step. Because in the original, remember, what is the infinite series? The infinite series is a limit. The infinite series is a limit of finite sum. So imagine if you replace infinity to some finite number, big N, and just let n tends to infinity. So in this definition of the infinite series, you're adding term consecutively, and just let the biggest index to go to 0. But here, after rearrangement, you change the order of summation. So in the first series, you're adding the even terms one by one, and then take the limit. And in the second term, of course, you add the odd index term and put them together. So this is a rearrangement. Once again, this requires justification. This requires justification in analysis. You have to say, okay, because this converges absolutely. Actually, it converges absolutely. Yeah, that would be enough. Right? It converges absolutely, so we can do this rearrangement. But here, once again, we're going to ignore that issue here. All right. So yeah, and then we use the pattern here. So n even can be written as follows: k from 0 to infinity minus it to the 2k, it to the 2k over 2k factorial, and then plus the sum k from 0 to infinity it to the 2k plus 1 over 2k plus 1 factorial. And now you just apply this result, so we get the sum of k from 0 to infinity, I to the 2k, that's minus 1 to the k, t to the 2k over 2k factorial, and then plus the other sum, k from 0 to infinity, minus 1 to the k times I. And you can pull out the constant I to the front, and t to the 2k plus 1 over 2k plus 1 factorial. And we can recognize, oh, this is just the Taylor series for cosine and sine respectively. So you get cosine of t plus I sine of t. That's not the derivation. Once again, this is not a proof because the Taylor expansion that we quote-unquote use is not an application, because this only works for real variables as far as our knowledge is concerned. Actually, we never really defined what is, say, e to the z for z complex. But inspired by these, you can make the following motivated definition. Okay, so yeah, the bottom line is, why is the complex number description in a sense better than the matrix form, than the matrix version? Because a rotation matrix needs 4 numbers. The 4 numbers, of course, they are constrained, right, because of property 1, orthogonality and length 1, orthonormality. Right? You need 4 numbers to write down a rotation matrix, but for complex number, you just need e to the I theta, just 1 number, e to the I theta. So e to the I theta is rotation counterclockwise by, you can say this, e to the I theta means rotation by theta, counterclockwise. So you just need 1 number, so that's very convenient. Just you remove the unnecessary degrees of freedom. Okay. Oh, sorry, that's not the right way to put it. A 2D rotation only has 1 degree of freedom. Only 1 free parameter, theta. And the complex number is especially efficient to encode that. Of course, this is because the multiplication structure, quote unquote, is baked into the definition of complex multiplication. Whereas for a general linear transformation, there is no such requirement. Another way to see that 2D rotation only has 1 free parameter is as follows. So you can look at the rotation matrix. You look at the rotation matrix by property 1. Okay? If a general matrix, say, just a 2x2 matrix, okay? If the general matrix satisfies the properties that the columns are all are all unit vectors. The columns are all unit vectors and they're orthogonal. That means you have three equations to satisfy. The first row, the first column being a unit vector. That's one equation. A11 squared plus A21 squared equals 1. Second column being a unit vector. That's another equation. And you need orthogonality. That's dot product equals 0. That's three equations. So if you have, intuitively speaking, so if you have four numbers and three equations, that's three constraints. So only one is free. Okay, so there's that. Okay, so that finishes pretty much the discussion on 2D rotation. Okay, and now we're going to discuss 3D rotation, which is significantly more complicated. And there are many different ways, okay, more than two, certainly, of how to describe 3D rotation. We're going to look at two formalisms, 3D rotations. First is still the matrix vector formalism, which in my opinion is perhaps the most intuitive. Vector matrix formalism. And the second would be the quaternion formalism. And the quaternion formalism is particularly popular in graphics engine and game engine development. Existing libraries are coded using quaternions. Okay, but it is less intuitive than the matrix vector formalism. It's kind of like in a 2D situation, right? You have the rotation matrix and the complex number. Complex number is perhaps more abstract. But hopefully we motivated everything. Okay, it is much harder to motivate the quaternion formalism. It's much harder to do that. And actually, I'm not an expert in algebra. I'll be completely honest. I don't know even a good way to motivate the quaternion formalism. And perhaps that's not a pathology because Sir William Hamilton, the inventor of quaternion, reportedly spent over a decade on finding an algebraic encoding of 3D rotation. Okay, so it is a very difficult notion. Okay, but I mean, it's not difficult for us to apply the formulas. Okay, I can just tell you the rotation formula in terms of quaternion, and you can certainly work with it. But I think it does not do justice to the amount of labor that went into this. So let's take a look at perhaps the most intuitive formalism first, vector matrix formalism. And before looking at the general case, let's first do some special cases. So let's say this is a 3D space, x1, x2, x3. And let's just describe the rotation with respect to each individual coordinate axis. Because even after we develop the general formula, we can still check whether our general formula makes sense by using those special cases. So it's not a waste of time. Okay. So a 3D rotation needs a rotation axis. It needs a rotation axis and an angle. So you need an axis and an angle to describe the rotation. Can be described using an axis and an angle. And this is called the axis-angle description. Pretty self-evident. Of course, Even though this is geometrically intuitive, it is at least not clear from the start that how do you convert that into coordinates? How do you compose that? Okay, so let's say if you know this is a general axis and you know the angle of rotation, how do the new and old coordinates relate? Right? So it's not trivial. Just like in the 2D case, right, we know that in the 2D case to describe a rotation, you just need the angle. But it's not trivial how that is expressed in Cartesian coordinate, right? Because you need this trig identity to do that. So yeah, thank you so much. This is what I wanted. I will watch. Thank you very much. Yeah. Don't worry. We will just go through the material in very much the same speed we've done earlier. And if we need another stream, we'll do another stream. Because right now I'm on vacation from, well, real life obligations. So I have a little bit of time to do this sort of thing. So here, I was saying that even though if you have an axis, say, to describe an axis, you need a unit vector, say n with n unit vector, the axis. If you have an axis and you can also put the rotation angle, say theta, but it's not clear how the old coordinate and the new coordinates relate. Right? So the vector matrix formalism is for that purpose precisely. It's to get a formula that that you can use to calculate the new coordinates from the old coordinates once you have the axis and angles specified. Okay, so now let's look at the special cases. There are few special cases that are readily obtainable just from 2D rotation alone. You think of it this way. So if we have just, oops, I don't like it. Let me just use this. Damn. Okay, I want to use this diagram, reuse this diagram. Okay, so let me just consider if the rotation axis is just x1. What do we write the transformation? How do we write the transformation in a matrix vector format? So yeah, if let's say this is a rotation about the x1 axis, okay, and this means every vector that is orthogonal to x1 can be treated as a vector living in the plane x2, x3. So this is essentially just a 2D rotation because x coordinate will not change. But special cases. Axes are just coordinate axes. Oh, thank you very much. Welcome to uniform. Okay. Yeah, that's the tier 1. Also, we covered geometric algebra. Actually, there's already a lot of good material on geometric algebra, and I hate to say this, but I'm not going to cover geometric algebra because simply I don't have the time to learn it. Okay, I don't have, and for me, like right now, the priority are very much elsewhere. Okay, this was intended to be a one-off stream, but I was very glad about the good reception. But here, I'm just saying that there are already many good channels on geometric algebra, and they have way better visualization than I do. Okay, perhaps it's just a difference in philosophy. I like to do everything from a scratch pad. I would like to draw my diagrams on the scratch pad. And just the old-fashioned way. Perhaps you guys, I can point you to good resources on geometric algebra. It's just I personally never learned it because I didn't quite feel the need to do that. I feel like, okay, seems like it can already do. I'll be completely honest. It might be a biased opinion. It feels like geometric algebra does not bring terribly new features that I particularly want it. Okay, I feel like the other things in mathematics already can do that. Okay, but this is not a dismiss of the subject. Okay, um, geometric algebra is still not mainstream. Okay, that does not mean it is useless. I don't find it interesting enough for me to spend significant amount of time to relearn it, to relearn the geometry using the geometric algebra formalism. Okay, I'm sorry. Okay, but that's just my honest opinion. But I will give resources on that subject. I'll put it in the comment after I finish the stream. So here, there's a special cases rotation about x1 axis. What is this t? About x-axis by angle theta. Well, you just need to change x1, x2, and x3. So x1 prime, the new vector x1 prime will have x prime equals the original coordinate. So if we rotate about the x1 axis, x1 does not change. And in the plane x2, x3 is just a 2D rotation. So you just apply the 2D rotation formula. So x2 prime, x3 prime equals cosine of theta minus sine of theta. By the way, Ansh, if you haven't joined my Discord server already, please, if you are interested in geometric algebra, there's a few folks, at least as far as I know, that are also interested in geometric algebra, and you guys can have fruitful discussion there instead of with me, okay? Because I am rather ignorant. Okay, times x1, x2. Okay, so yeah, that's the rotation matrix in 2D, and we just import it here. And of course, we can combine everything into three-dimensional vectors, which is equivalent to x1 prime, x2 prime, x3 prime equals 3 by 3 matrix given by 1, 0, 0 cosine theta minus sine theta 0 sine of theta cosine theta and 0. No, this is not good. This is terrible. Sorry, my bad. This is if this is true, then it's a singular matrix. Okay, anyway, here. What I mean is this, okay? That wasn't good. So yeah, that's the rotation matrix about x1. Okay, x1, x2, x3. So we may denote this as r x1 comma theta. So this is rotation about x1 and angle theta. And similarly, you can repeat this, okay, and derive the rotation matrix about the other coordinate axes. Okay, say this is x1, x2, x3. Okay. Special cases. This is rotation about coordinate axes. All right, so yeah, let's just do the others real quick. Okay. And you get, by x2 axis, let's draw the diagram first, as usual. So it should look something like this. So the non-trivial part happens in the x1, x3 plane. So x1, x3 changes according to the two-dimensional rotation. Perhaps it is more efficient to simply write cosine as C and sine as S. Okay. But you know what, I'll do it fully. And these notes will be uploaded after the stream is done. Okay, and x2 does not change. Put that into 3 vectors. You can see here x, remember, let's just put x1, x2, x3 first, okay, and then fill in the coefficient. This way is less likely to make mistakes. x1 has a coefficient of cosine. x3 has a coefficient of minus sine. And it's got nothing to do with x2, so we put a 0 here. So x2 prime is just x2, has nothing to do with x1 or x3, so you get 0, 1, 0. And the last row would be cosine of theta, sorry, it should be sine of theta. Sine of theta of 0 and cosine of theta. Right. That's rotation about x2. Okay. Let's put all these diagrams together. Okay. And the last case would be rotation about x3. So these are baby steps we can make. By theta. Okay, so rotation about x3, so there we go. So everything interesting happens in the x1, x2 plane, the horizontal plane. The x2 diagram should have the arrow starting from x1 axis. Hold on, Bruno says x2 diagram. Yeah, so from x2 to x3, right? This is the arrow. Did I make a mistake? This is weird. Yeah. Okay. I'm glad we're on the same page. So x3, look at this picture. x3 is of course fixed, and x1, x2 changes according to the 2D rotation matrix. So far everything is very natural. Okay. I'm just going to copy this expression and change the index. Save a little bit of a writing. And x3 doesn't change. And in engineering, this is already a great way to describe motions of like a spacecraft or aircraft. I'll just show you a quick picture real quick. After I finish writing this stuff, these are called the yaw, pitch, roll angles. And there are certain canonical choices for the axis directions. x1 prime, x2 prime, x3 prime. Just going to finish writing the formulas. This should be straightforward. Cosine theta minus sine theta, 0, sine theta, cosine theta, 0, 0, 0, 1, and x1, x2, x3. Okay, so here, of course, we denote the second matrix to be Rx2 zeta, and the last one being Rx3 zeta. Also called the Euler's angles, because, well, Euler's angles are more general. The rho, pitch, yaw are specific examples of the Euler's angle. Okay. Now I'll talk a little bit about Euler's angles as well. Okay, but first I would like to show the picture for the three diagrams here. Okay, let me just go search up the image. So yeah, here's a nice picture. Hold on a second. What? Yeah, that's the picture. You see, what did I just do? What did I just? Oh, dang it! My God, please don't die on this. I like that. Uh-oh, guys. Okay, I don't know what happened. Okay, is everything I wrote still there? Hopefully. Okay, so it looks all right, but where's the picture? Okay, for the fighter jet. Okay. Okay. So yeah, these are the canonical choices for the roll, pitch, and yaw, pitch, roll angle. Okay. Which is our special cases of Euler's angle. Okay. Since it is mentioned in chat, don't be sorry about what. Anyway, here let me just briefly draw the Euler's angle. Because in Euler's days, geometry was still done mostly through analytic means. Yeah, maybe control plus A by accident. Yeah, Euler's angles are defined as follows. So imagine you have an orthonormal basis like this. Perhaps I should use. Okay, let me draw things a little bit differently. So here, this is the laboratory frame. I'm borrowing terms from physics. So this is fixed. Okay, this laboratory frame, and then you have coordinate axes, not coordinate axes, but a set of orthonormal bases. So say you have a set of orthonormal, but originally aligned with the lab frame. Let me copy that a few more times. I need 3 copies of these. Oh, okay. I need another copy. Another one, yeah. So Euler described 3D rotations in 3 consecutive with 3 consecutive rotations. Okay, so you have, let's say this is the original configuration. Okay, let me actually use sticker lines to distinguish it from the coordinate axis. So this is the original basis, like this. Orthonormal basis, just like E1, E2, E3. And then you rotate it. We fix the vertical axis. You rotate about the vertical axis first, and you get something like this. So the vertical part stays constant. That doesn't change. I know this is horrible looking, but perhaps I can move it a little bit. Perhaps this is okay. This is okay. So you are rotating with respect to the vertical line, and the angle is theta. So that's the first, actually, that's called phi. That's the first Euler's angle. And then you do what? And then you treat the rotated frame as the new frame of reference. Okay, so here you're keeping, in particular, let me just copy this to indicate this is fixed. Okay, this vector is now fixed. For the sake of next step, this is fixed. And rotation is done about this axis. That's the new axis. Okay, so that's a new axis. There you go. And the angle is theta. So as you can imagine, here these two vectors no longer align with any coordinate axes anymore. Okay. Purely because of you wanted to maintain orthogonality of the basis. So the three red vectors remain orthonormal. See, here, that's the original position of the vertical vector, and the rotation angle is denoted as theta. This is theta. Okay. All right. Okay. And lastly, we treat this vector, this particular vector, as the final axis. Put it here. Okay, so that's the new axis now. So this is a way to describe a general 3D rotation. So we're on our way towards describe should the rotation about X2 matrix actually be. Oh, hang on a second. I'll take a look. Okay, I might have made a mistake. Sorry about that in advance, but we'll take a look. Okay, let me just finish drawing this picture. Here, this is a new axis, and that's the old direction of this vector, and it gets rotated like here. Perhaps it's a good project to animate this, and like this. That's not a good idea. Like this. Okay, and that angle is phi. Hang on, let me just extend things a little bit, and that is psi. That is psi. If there's any group theory, not today. Each row above, sorry, can't type it properly. I know, right? I'll take a look. So here, you're talking about the rotation about the X2 axis, right? This one, the middle one. X1 prime is cosine theta times X1 plus 0 times X2. Your tachyon says, should the rotation matrix about X2 actually be cos theta y? It should be a minus sine theta. Hold on a second. Is there? Let me actually. You know what? There's a link in the stream description. There's a link in the stream description. I'm just gonna check it real quick. Hang on a second. All right. Let me just look that up real quick. So if you guys go to the stream description, there's There's a link under that's rotation matrix in Wikipedia.
Let me just
Rotation matrix. Let me just go check that out here.
look that up real quick. So if you guys go to the stream description,
What is this?
there's
Into the other screen. I don't know.
there's
why.
a link
Here,
under that's rotation matrix in Wikipedia.
What about rotation?
Let me just
Rotation matrix. Let me just go check that out here.
look that up real quick. So if you guys go to the stream description,
X2 is our y-axis.
what is this?
There's
There's
into the other screen. I don't know.
there's a
why.
link
Here,
under that's rotation matrix in Wikipedia.
What about rotation? So
Let me just
matrix. Let me just go check that out here.
look that up real quick. So if you guys go to the stream description,
X2 is our y-axis. You should
what
use
is
the
this?
right hand.
There's
Because here
the
at
other
the end
screen.
will say
There's a link under that's rotation matrix in
Thank you so much for
Wikipedia.
what about rotation? It's a right hand.
Let me just
matrix.
let me just go check that out here. Look that up real quick. So if you guys go to the stream description,
X2 is our y-axis. You should
what
use
is
the
this?
right hand.
There's
Because here
the
at
other
the end will say
screen. There's a link under that's rotation matrix in
Thank you so much for
Wikipedia.
what about rotation? It's a right hand.
Let me just matrix. Let me just go check that out here. Look that up real quick. So if you guys go to the stream description,
X2 is our y-axis. You should say
what
that
is
the
this?
right hand.
There's
Because here
the
at
other
the end will say
screen.
that
There's a link under that's rotation matrix in Wikipedia.
what about rotation? It's a right hand.
Let me just matrix. Let me just go check that out here. Look that up real quick. So if you guys go to the stream description,
X2 is our y-axis.
what is this? There's
Because here
the
at
other
the end will
screen.
say that
There's a link under that's rotation matrix in Wikipedia.
what about rotation? It's a right hand.
Let me just matrix. Let me just go check that out here. Look that up real quick. So if you guys go to the stream description,
X2 is our y-axis.
what is this? There's
Because here
the
at
other
the end will
screen.
say that
There's a link under that's rotation matrix in Wikipedia.
what about rotation? It's a right hand.
Let me just matrix. Let me just go check that out here. Look that up real quick. So if you guys go to the stream description,
X2 is our y-axis.
what is this? There's
Because here
the
at
other
the end will say
screen.
that
There's a link under that's rotation matrix in Wikipedia. Let me just
Okay, yeah, I opened my own stream. That's the reason. Sorry. Yeah, you're hearing the stream because I open it up to check the link in my description. Hang on. Sorry. Is it better now? Because I closed my own stream. Yeah, the audio is just. How about now? Can you hear anything? Still no. Is it okay now? Yeah. I opened up I opened my own stream to get to the wiki link. That's why. Because somebody said it's wrong because I actually look at the answer, okay, in the Wikipedia. Indeed, I was wrong. And that's because of the right-hand rule thing. It's working now. Thank you so much. Okay. Okay, great. Sorry about that. So, all right. So let's rewrite the rotation matrix. So x3, you see, x3 now serves as x1 in the 2D case. x3 in the 3D case and serves as x1 in the 2D case. All right. So let me rewrite that. Very nice. Thank you so much, Tachyon, for pointing out the mistake. x3 prime, x1 prime works like rotation in R2. Okay, x3. The orientation was messed up, so the minus sign location is messed up. Everything now should be fine. Okay. You fixed it when you closed the stream, so I was sure that was that was the problem. Okay, So yeah, that's the Euler angle formulation I was talking about. So it's a sequence of transformations. The Euler angles phi, theta, and psi. Okay, but that's not our focus here. Our focus is still aimed to derive a coordinate representation of the coordinate in terms of Cartesian coordinate, right? So these are different ways to parameterize a general 3D rotation, but we still need the matrix. Okay, so mathematicians always thank you for pointing out the mistake is dope. Of course, like you don't want your work to have mistakes, right? It takes work from on behalf of other people to spot your mistake, and in general, getting feedback in mathematics is very difficult, you know. So this is not a trope or anything. I'm just genuinely glad that such a mistake was caught. This is amazing. Anyway, so here let's get to the derivation of the so-called Rodriguez formula. Rodriguez, how do you spell that? My goodness. Let me take a look at my notes. Rodriguez formula, rotation formula. So this is general rotation. A rotation about a general axis and a general angle. Before we were just doing rotations about coordinate axes. This is a rotation about a general axis specified by n. N, this is a unit vector. And you define rotation in accordance to the right-hand rule. A general axis and a general angle. Which is theta. Okay, so let me just draw the picture. So I will not draw the coordinate axes anymore, because right now we're not using coordinate axes. Visualization for that is just introducing extra noise. So let's just call this n. Okay, I don't imply this is a vertical axis. It's just a general axis. And what we want to do is to describe the new vector. Okay, this is the old vector, by the way, this is x. And then you rotate it as follows. Okay, perhaps I should make things a little bit more pronounced, because the two vectors nearly have the same direction. That's not good in the picture. So, okay, so first of all, let me draw a circle here. So this is the unit vector n. This is a ellipse on the plane, but it's meant to be a circle in the 3 space. And here you have a general vector x, and here we wanted to describe the rotated vector x prime. And if we look at the angle between the perpendicular component of x and x prime relative to n, they form an angle of theta. So we wish to give a formula for that. Okay, and to do that we need some tools from vector algebra. We need some tools from vector algebra and their properties. So let's review that first. Okay, a review of cross and dot product, dot and cross product, just to make sure everybody's on the same page. Dot product and cross product. Hold on, can't spell. Yeah, so the goal is to, yeah, as I was saying, the goal is to express x prime in terms of three things. In terms of x, n, and theta. So n and theta together, we haven't written that down yet, but n and theta together defines the rotation operator. Because it's intuitive. If you're given an axis and an angle, the transformation should be well defined already. Right? So n and theta together defines the operator, rotation operator. Okay, so we wish to find a formula for that, and the outcome should probably look like this. So x prime is a linear transformation, r and theta times x. So we just need to figure out the matrix r and theta. So this is what the Rodriguez formula is about. Okay, so to do that, let's first review the dot product and the cross product. So first of all, dot product. So here everything is in R3 now. Let x and y be in R3. Three vectors. So what's the dot product? X dot y. X dot y is, let's first derive everything geometrically before we give the coordinate formula. So x dot y is the length of x times the length of y times the angle. This is motivated by work in physics. And also orthogonal projection in geometry. So what I mean by that is the idea is dot product only cares about the tangential component. The tangential component of a vector y onto another vector x, if that makes sense. So y times cosine theta is the projection, is the scalar projection. Let's call it. There doesn't seem to be a good notation for scalar projections. I have to just improvise, say scale pro. Okay, the scalar projection of y onto x is this thing. It can be negative because if theta is greater than half pi, the scalar projection will be negative. So this is equivalent of saying x length times the scalar projection of y onto x. So that's the dot product. That's the definition of the dot product geometrically. And of course, we can get a formula in terms of coordinates. And to do that, we need a few properties. So property. Just from this definition, the geometric definition alone, we can see, first of all, it is commutative. X dot y equals y dot x. It's clear from the definition. Because if you switch that, you just get the y, switch the order, you just get the y length times x length times the cosine of theta. Cosine of theta doesn't change. And of course, multiplying two lengths doesn't care about the order. Okay, so that's the commutativity of, or commutativity or symmetry in dot product, symmetry. In linear algebra, we typically say the dot product or the inner product is symmetric. All right, and you also have the other property. So basically, you can take out the constants. So to say, you can, let's say if you do c of x dot with d of y, c of x dot with d of y, and you can just pull out the constant. There's a cd times x dot y. This is also clear geometrically. From the formula. You need that cosine of x even since the theta should reverse sign if you switch the order. No, theta doesn't care. Theta, if you the order. So you mean theta is measured, say, from rotating x to y or y to x is not relevant because theta is even function. Yeah, you just mentioned, right? Theta is even function, so the orientation of theta does not matter here. Okay, but where theta is the angle between x and y, this does not matter. Right? For the dot product, it does not matter. For the cross product, it matters, but the cross product has its orientation defined by the right hand rule. Okay. So as I was saying that here, the second property you can take out constants. The third property is distributivity. So if you have x dot with y plus z, this is the same as x dot y plus x dot z. This is also true. Okay. Here, let me just try to find a diagram in my notes. Yeah, the distributive property. How do you visualize that? Now, so in general, x, y, and z are vectors in R3, so they don't necessarily live in the same plane. So let's draw a picture to verify, to illustrate the situation. So imagine this is the y and z plane, y and z vector, they live in the same plane. You can always assume that y and z aren't in the same line. Okay. This is y and z, and the plane they determine. Okay, and of course, use the parallelogram law. You can easily draw the sum vector y plus z. Because this is y plus z. Okay. What is x? Well, x can be a general vector which may not live in the plane. So this is x. So this is x, and we can, you know what? Let me extend x a little bit. Perhaps there's a more visually pleasing way to draw this. Okay, so on the left hand side you have x dot y plus z. So why don't we project y plus z onto the x direction like this? Okay, and so here you have this green line segment. Okay, from here to here is the scalar projection of y plus z on x. Okay, and what do we want? Okay, we want to see this is the same as x dot y plus x dot z. Well, for that you have to project y and z onto x as well. So projecting y onto x is as such, and projecting z onto x is as such. And this is purely because of scalar projection is additive. Okay, scalar projection of y plus z is the same as the scalar projection of y plus the scalar projection of z, providing you're fixing the axis of projection. Okay, yeah, this is true because the scalar projection of y plus z onto x is additive. Z to x. So that's the geometric meaning of the distributive law for the dot product. Okay, so these are useful properties, and we can use these properties to devise a formula for the dot product. Here, definition. Okay, and here we wish to derive the coordinate representation, coordinate formula. So for a coordinate formula, of course, we first do the basics expansion. X is written as x1 e1 plus x2 e2 plus x3 e3. Okay, do the same business for y. And you just take the dot product of the two. And we can use things like the distributive law and symmetry. Okay. X dot y is x1 e1 plus x2 e2 plus x3 e3. And by the way, in a few weeks, I think August 8th, in a few weeks, yeah, we'll do some tensor stuff. So in there we will save some writing. Okay. And that August 8th will be on information geometry. Information geometry, a research frontier for statistics and machine learning, but in this second half, actually more than the second half of the stream, would be focusing on just the fundamentals, okay, the fundamentals of differential geometry from a classical perspective. Okay, so there we will do some tensor calculus, and over there we can save some writing due to the summation notation. All right, so here we have this expansion. You can just take out the constants and do all those business. So you get x1, y1, these are all scalars. Okay, so let me just draw the picture here. So here, e1, e2, e3 are the basis vector. Okay, just to make sure there's no confusion there. E1 is the basis vector along x1. E2 is the basis vector along x2. So in vector analysis textbooks, they're usually written IJK. I know, right? A lot of courses, they just give the formula from the start, and then you prove things with it, which is certainly okay. But I prefer a more geometric approach. Right? You define the notion geometrically, you derive its properties geometrically, and then you derive a coordinate formula from it. Okay, that's my kind of thing. So you got x1, y1, e1 dot e2 plus x1. There should be in total how many terms? There should be 9 terms in total. x1, y1, x1, y2, e1, e2, and plus x3, y3, sorry, no, that's terrible. x1, y3, e1, e3. Okay, and the second expansion would be x2, y1, e2, e1, e2 dot e1 plus x2, y2, e2. Okay, I forgot the dot here. My goodness, that's not good. Just put the bracket here to indicate these terms we will calculate shortly. E2 dot e2 and x2, y3, e2 dot e3. And lastly, x3, y1, e3 dot e1. So A. Buckingham mentioned this is derived from bilinearity, exactly. X dot y, the dot product, is a special example, is an example of bilinear form. And in fact, we can write this in a matrix notation. We'll do that in a second. x3 dot e2 plus x3 y3 e3 dot e3. Okay. Okay. As I was saying, this can be written in matrix notation. So that's x1, x2, x3 Yeah, the first term should be E1. Yeah, E1, E1. You're right. You're totally right. Sorry. Thank you very much. Yeah, okay, everything looks fine now. X1, X2, X3 times the matrix E1 dot E1, E2 dot E1 dot E2, and E3, E1 dot E3. Okay. Why am I keep making these silly mistakes? Anyway, so E1, just gonna pay more attention. E1 dot E3. E2 dot E1, E2 dot E2, E2 dot E3, and the last row is E3 dot E1, E3 dot E2, and finally E3 dot E3 times the column vector Y1, Y2, Y3. Okay, so this is a matrix vector multiplication. You can write it as X transpose times the matrix G. Okay, this is a matrix G called the Gram matrix. For those who've taken linear algebra, probably heard of the term Gram-Schmidt procedure, or the Gram-Schmidt orthogonalization procedure. Difficult word. Yeah, this is called the Gram matrix. So in general, if you have a basis vector, a set of basis vectors, okay, it doesn't have to be orthonormal or anything. Say E1, E2, E3. That doesn't have to be orthonormal, and you can always form this matrix. And this matrix is called the Gram matrix. And this will actually play a role in our upcoming stream on information geometry. This is something called a metric tensor, in fact. So X transpose times G times Y. So that's the matrix form. But now it's just a matter of evaluating the Gram matrix. And this should be easy because due to the geometry, by the orthonormality of the basis, since E1, E3, E1, E2, E3 is orthonormal, the dot product EI dot EJ equals the so-called Kronecker delta, delta IJ. When delta equals 1 if the indices IJ matches, okay? If the indices IJ match, otherwise it's just 0. If I equals J, otherwise is 0. So that means the Gram matrix is the identity matrix. So therefore, G is just the identity matrix, 3 by 3 identity matrix. So X dot Y is just matrix multiplication, X transpose Y, which is a nice formula, and this is equivalent to, of course, X1, Y1 plus X2, Y2, and X3, Y3. As we can see, the cross terms here, the cross terms where the indices, the product in which the indices don't match vanishes because of orthogonality. And this is quite crucial here. In a general tensor analysis setup, you don't always work with orthonormal basis. And in those cases, you have to, for example, if you have a so-called affine coordinate, there's affine coordinate meaning the coordinate lines are still straight lines, but they aren't necessarily orthogonal, in which case the dot product would have to include cross terms. Okay, so that's the familiar formula of the dot product. All right, so yeah, that's the dot product. And now let's take a look at the cross product. Okay, the cross product is also highly useful. It perhaps one of the, you can argue that the cross product was invented because of the dot product is not very effective when it comes to describing rotation. So cross product, perhaps, yeah, somebody asked me earlier that the question whether the cross product or the dot product is more important. Well, if you if we're just talking about rotation, I would say cross product saves the day. You can't. I mean, I've never tried this before, but you can probably use dot product only to describe rotation, but it's not going to be very efficient. Okay. All right. Well, we just get to the definition of dot product. Hopefully the cross product. Okay, cross product is defined as follows. Once again, this is a review. Just want to, because I never given any examples, right? So just want to review these concepts, but at the same time, I don't want to feel like these are dropped out of the sky, dropped from the sky. Okay, so that's the OpenGL transform object is an affine matrix. It's extremely useful in practice. Nose product in 4D is not as general. Exactly. So cross product is purely an artifact in R3. It works only in R3. As far as I know, okay, I never proved it, okay, and perhaps it's go ask an algebraist if you wanted to formalize a statement that a cross product it only works in R3. But in arbitrary dimension, there is this notion called exterior product. Exterior product is related to things called differential forms. But anyway, here we're just talking about R3, not arbitrary. We're not going to generalize things at this stage. So just to keep everything fully motivated and visualizable. Okay, so now, once again, we're still working with X, Y, and R3, as usual. Oh, actually, I forgot a property which should be useful. X dot X with itself is square norm. Okay. Cross product. There's a 70 cross product, but well, that's it. Okay. I didn't know. Thank you very much for pointing that out. Here you have X and Y in R3. Theta, as usual, is the angle of X and Y. Once again, there seems to be a little bit of confusion, right? Because the orientation dictates the sign of theta. So why don't we just fix that and say this is the angle needed to rotate from X to Y. This is theta. Okay, and to define the cross product, we would need to use the right-hand rule. To find it physically, you need the right-hand rule. Mathematicians, pure mathematicians, tend to avoid the term right-hand rule because the right hand is not a mathematical object. But I figured there's no need for such level of formality for this live stream. So here we have X and Y vectors, assuming they're not collinear. Okay, if they're collinear, then the cross product is easy, simply 0. Assume you have X and Y, as we shall see shortly. Okay, it's not an arbitrary definition. But here, let's assume that X and Y are not collinear, so they determine a plane. And the cross product X cross Y is a normal vector of the plane. So this is X cross Y. And of course, there's a question, does it point up or down, right? So, but that's answered by the right-hand rule. So let me just draw a right hand. Hopefully this doesn't look too terrible. Yeah, so that's the right hand. Okay, so that's, oh my God. Okay, this is the right hand. Okay, so yeah, that's the cross product, or sometimes called the vector product. So if, let's say, z equals X cross Y, if z has a magnitude means z, the magnitude of z is the magnitude of X times the magnitude of Y times the sine of theta, absolute value times the absolute value of sine of theta. Because this is a subtle point. Because theta as an angle between two vectors is treated to take values between minus pi to 0. Sorry, minus pi to pi. Minus pi to pi. Okay? And actually, I'm not sure which it should include. It should include. Okay, you know what? It doesn't matter. Let me just keep one. Okay, let's keep the angle pi to be attainable and minus pi to be unattainable. So this way there's no ambiguity. So when the angle between the two vectors is pi, that means they're just in the opposite direction, and we exclude the value minus pi. It's purely artificial. And here, in that range, theta can take negative sign value. And of course, the magnitude is always non-negative, so we take the absolute value of sine of theta. There is no need to do that for the dot product because cosine in that range is always positive. No, I'm talking nonsense there. Oh, there's no need because cosine is even. Cosine is even, and the interval is symmetric. Not because cosine is always positive. Dot product don't have to be always positive. Okay, it does not matter. As I was saying, it does not matter the orientation of theta here. Okay, you can rotate x and measure the angle that you need to get to the direction of y, or the other way around. It does not matter, but it matters for the cross product. Now, cosine is you solve the problem exactly, and sine here it takes. It's an odd function. Okay, and z is perpendicular to the span of x and y. I'm using the linear algebra term. Okay, the span of x and y is this plane. Z is perpendicular, and z is direction has direction according to the right hand rule, as shown. There's that. Actually, there's a nice interpretation of the magnitude because x times the x length times y length times sine of theta absolute value is the area. This is the area. So numerically, the length of the vector x times y equals the area. Right. So perhaps I wasn't very appreciative of the of geometric algebra, as it was stated earlier, but I do concede that in geometric algebra you don't have cross product. Instead, you have a bivector, right? Is it generalization? Probably not, but I don't really care. Okay, because I don't really care because there's this notion called exterior product, which does work in n dimension, and it's not quite as a generalization, but it's good enough. Okay, so I was saying that, and following on that, because exterior, so the cross product encodes area. See, that's the same. Cross product encodes the area, and that's exactly what exterior product does in arbitrary dimension. Okay, we're getting way ahead of ourselves, but that's why the generalization of cross product into n dimension is not really interesting to me. Geometric algebra, as far as I know, okay, please do correct me if that misunderstood that. There's no such thing as x cross y, but rather you call that a bivector. You call that a bivector, and which makes sense to me because you see x cross y from a purely dimensional perspective. It should not live in the same space. It should not live in the same space because imagine x has a unit of length, y has a unit of length, x cross y should have a unit of length squared. Of course, that's an area, and it seems rather arbitrary to force it to live in the same space as x and y. It is defined because a physicist likes it. The quaternion, I mean. Right? So the quaternion it's not really a generalization of the cross product either, because quaternion is a four-dimensional object and there's no cross product in 4D. Okay, can we just stop thinking about? I'm begging you. Okay, stop thinking about generalization of the cross product. It's I would say it's defined by physicists. Okay, it's defined by physicists because it's useful to describe things like the torque. Actually, torque is kind of arbitrary creation, but I'm talking about the Lorentz force. Okay? The Lorentz force for in electrodynamics. So the cross product actually has a physical meaning there. So physicists liked it and kept it that way. So there was actually a huge controversy at the turn of the 20th century over quaternion or vector analysis. Okay, well, vector analysis. Vector analysis was invented by Gibbs. So Gibbs was famous for his contribution in statistical mechanics, the Gibbs distribution. Also in, nowadays the Markov chain Monte Carlo folks use a lot of the Gibbs sampling. But I was saying Gibbs invented the modern vector analysis, dot product, cross product, and formulated those and became popular. But at the same time, there were folks who are more invested in the quaternion formalism because quaternion was developed earlier. And in a sense, and let's be honest, quaternion subsumed. I'm not even sure if we can get to quaternion today, which is a bit of a shame. But I mean, that's okay. And then again, quaternion subsumes the dot product and the cross product. But it also has so many other features that aren't really physical. So physicists discarded the features that aren't physical and kept the dot and cross product. So there was a huge controversy back then. Mathematicians who felt that physicists who destroyed the unity of the quaternion were outraged, and there was this competing formalism between the quaternion and vector analysis. That's called the vector algebra war, if you go search it up. But eventually, quaternion kind of faded into relative obscurity, except as an important example in abstract algebra and in rotation. So practically speaking, perhaps rotation is the only relevant area application nowadays. Okay? But in the late 19th century, there was a serious attempt to consider to make quaternion the main formalism of physics, but it didn't really stick. It didn't really stick around. So, but eventually the dot product, cross product formalism went out historically, and now, of course, generalizing the dot product gives us the inner product, and then you got the Hilbert spaces, which was hugely successful in quantum mechanics, and so basically quaternion died in physics. Anyway, that's too much digression. Let's come back to the cross product. Okay. Anyway, hopefully we can put a pause on our temptation to generalize the cross product. It's really just an artifact in R3. Okay, so here we have the definition of the cross product, and you have a bunch of properties. In contrast to the dot product, the cross product is anti-symmetric, meaning if you switch up the order of the argument, the sign gets flipped. And this immediately implies if you cross a vector against itself, you get 0. All right. And we also have the taking out constant property, C times x cross d of y equals not minus, but just CD times x cross y. Okay, so there's that. And once again, these properties are easily obtainable from this geometric definition. Because let's say, for example, if you just want the anti-symmetry, this is anti-symmetry. you would have to rotate y so that its direction align with that of x, right, using the right-hand rule, and the product would point downwards. And because the magnitude is the same, so it's just minus y cross x. Okay, so all these properties can be shown geometrically. And also you have the distributive law. So that's x, which is a little bit harder to show. X cross y plus z is x cross y plus x cross z. Okay, that's the distributive law for the cross product. It looks natural, but showing it is actually not that simple. Okay, it's perhaps useful to note that the cross product cared about the orthogonal component as opposed to the dot product. The dot product cares about, after you do the vector decomposition, the dot product cares about the tangential component. It's like in physics, if the force is perpendicular to the displacement, then it does no work. That's why in a circular motion, the centripetal force does no work, because you always have orthogonality. But here, in the cross product, what we really care about is the orthogonal component. So it's the orthogonal component of y times the length of x. So if we can write it that way. Once again, there's no standard notation for that. So let's just say y times y absolute value times theta absolute value is the scalar orthogonal component. I don't know how to say it, but you get the idea. The height, right? Something like that. Scalar, or just actually, you know what? Just this is because this is a non-negative, so it's just the length of the perpendicular. That's okay. The perpendicular of y relative to x. So the cross product cares about the perpendicular component, and if you take that into account, if y and x are in the same direction, the parallelogram collapses to a line, and of course the area is 0. All right, so let's draw the diagram to illustrate the distributive law for the cross product, shall we? Here's a little proof. Because everything is so far defined geometrically, we need a diagram. So I'm drawing a plane, and this plane is the one that is orthogonal to x. As I was saying, we want the orthogonal component of y plus z onto x, if that makes sense. All right, so let's draw a little plane here. Desmond will help me out. Can you straighten this up? Yeah, thank you very much. And this is the vector x. Okay, this is a vector x, and the plane is orthogonal to x. You can always construct that plane. And this is the origin. Okay. So here, let's draw the vector y as such. Say this is y. And then for the ease of creating the vector sum, let's just call this z. Okay, I put the starting point of z at the end point of y. This is z. And of course, here you have the triangle law for vector addition. And this is y plus z. So this is y plus z. All right. So what is the left-hand side? Well, we need to get the perpendicular component of y plus z relative to x, which is equivalent of projecting the. Hold on a second. Projecting. Yeah, we need to project all three vectors, y, z, and y plus z, onto the plane. Right, this is P. Say P is plane P is perpendicular to x. Let plane P be perpendicular to x. You can always do that if x is non-zero. And hold on a second. Let me
project that.
Okay, so the projection should look something like this. Let me change the color. Hold on. So let's say y is projected to be this vector onto P. And y plus z is projected to be this vector. Okay. Can I get a straight line, please? Yeah. So that's the projection of y plus z. And of course, the projection of z is just connecting these 2 points. And let's give them some letters, shall we? Let's call here this point big Y, because that's a projection of little y. This is big Y. And here you got, this is Z, you know what, let's just call it big Z. Call it big Z, okay? And now, what do we do? What's the cross product, remember? The magnitude, first of all, the magnitude of the cross product is the perpendicular component gets scaled by the length of x. So here, the projected vector y perpendicular and z perpendicular and y plus z perpendicular, we want them to be all scaled by the length of x. So let's do that. And because of the scaling is the same, the scaling constant is the same, so you get a similar triangle. So once again, we're using a lot of high school geometry here. So this is a scaled version of these projected vectors. All right. So let's just call those points, new points. Let's call this point, say, what would be a good letter? I don't know. Let's just call it E, D perhaps. Okay, so let's describe these vectors. So let plane P be perpendicular to x. OY, the vector OY is the projection, or the perpendicular. Let's use the perpendicular. The perpendicular of y vector relative to x. Okay, this is OY. OZ, actually OZ is the perpendicular of y plus z. Yeah, the wedge product, you could do cross product in 4D provides, okay, generalized, okay. 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 So, I mean, thanks for the input, but I don't really care about the generalization at this moment because that's just distraction at this point. Anyway, of course, these are fantastic topics. Like exterior products, differential forms are very beautiful. And YZ is the perpendicular component of Z relative to X. Okay, so these are these vectors, and we'll define the scaled vectors too. So OD, actually OE is OY times the magnitude of x. I was meant to introduce geometric algebra. You see, geometric algebra has a lot of fans online. Very dedicated. Once again, this is not a sarcasm or anything. I'm just genuinely interested about this fact rather than geometric algebra itself, if I can say it that way. Because once again, I'm not disparaging geometric algebra in any way. Just as far as my main area of work, I find the existing formalisms such as tensor and differential form to be sufficient. Okay, but of course, go ahead and pursue geometric algebra. A lot of things were in mathematics history were underappreciated. Okay, so OE was OY times X length. So it's fascinating, isn't it? Like, still, like the vector algebra war, as I was mentioning, at the end of the 19th century, continue on to this day, in a sense. I remember the inventor of geometric algebra was rather critical about the establishment when it comes to refusing to take new ideas seriously and whatnot. I forgot his name, but yeah. So thank you very much. Lockheed Martin as our Blackbird. Okay, that's a cool name. Thank you very much for bringing this up. So OE is OY scaled by the magnitude of X. OD is OZ scaled by the magnitude of X, as yeah. And lastly, DE is Y, ED probably. ED. ED is YZ gets scaled by X. And once again, because the scaling factor is the same, you got a similar triangle scenario. So that is, I'm saying ODE is similar, triangle, is similar to OZY. Similar triangles. Can't believe we're doing similar triangles here. I haven't touched high school stuff in a while. All right, so here we have OE. What's the length of OE, right? Why do we even consider this? Because OE magnitude, the magnitude of OE is, hold on a second, the magnitude of OE, just purely from a magnitude perspective, okay? It's not the cross product itself, but the magnitude of OE, because OY is, okay, OY is the perpendicular component of Y onto X, so OE length is X cross Y. Is the length of X cross Y, because OY is a perpendicular of Y onto X. Then you do the same for the rest. OD has a magnitude of X cross Y. Remember, OZ is the projection of the sum, so or the perpendicular of the sum. So OD length is the length of X cross Y plus Z. Sometimes also share the sentiment vector algebra was a bad choice down the line. Yeah, the thing is, when you make a definition, you always make compromises. I mean, I like certain things about vector algebra in the sense that keeps the essential part of the quaternions as relevant to physics. Because quaternions has too many structures, let's be honest. Right? I hate cross product with a passion. Yeah, it's a very polarizing thing. Right? I mean, I don't think a lot of people hate dot product because it generalizes naturally, right? And all those Hilbert space stuff is so formidable to argue against. But cross product, being the artifact of R3, suffers a lot of criticism. Totally understandable. So ED is what? ED, the length of ED is the length of X cross Z. Right. So far, this is our construction. And now what do we do? Well, think about it. Think about what is the orientation. Think about what is the orientation of the cross product. Let's think about X cross Y. Okay, X cross Y. Here, X cross. What is X cross Y? X cross Y. If you use the right-hand rule, it's easy to see that X cross Y is perpendicular to the plane determined by X and Y. So X cross Y should be somewhere like this. So this should be X cross Y. Okay, I might need to enlarge this plane. Okay, hopefully this is all right. And yikes, because this is a really long node, and one node is getting sluggish. Okay, so I slightly enlarge the plane to make drawing more comfortable. And the main point is x cross y is perpendicular to both x and y. And it should be in this direction rather than the opposite direction due to the right-hand rule, x cross y. So as we can see, x cross y must be in plane P. Right? First of all, x cross y is perpendicular to x. The cross product, remember, by the definition of cross product, is perpendicular to both vectors, taking cross product. So that's why here, x cross y being perpendicular to x must lie in P. Let me write that down. Since x cross y is perpendicular to x, x cross y lives in P. Okay, it lives in P. And in fact, it is also, by the fact that it is also perpendicular to y, it is also perpendicular to OY. Correct? X plus y, it is also perpendicular to OY. Because OY lives in the same plane as y and x. Since OY is the perpendicular component of y relative to x, not OP, OY. OY, it's been a while since I did a proof in classical geometry, a la Euclid, without using coordinates, okay? So this is fun. So OY is in the span of x and y. So OY is the span of x and y, and since x cross y is perpendicular to the span of x and y, x and y, okay, x and y, x cross y, or x cross y must be orthogonal to OY. So that's why I put a perpendicular sign here. So this is justified now. And of course, the same business can be done for the other sides. And let's draw them as well. So this is x cross y. And as we mentioned, x cross y has the same length as OE. Right? OE, x cross y, and OE has the same length. This is a rotation. This is a rotation on the plane P. Okay, and we do what? We do this. So here, what we get is, this is a rotated version of OD. Can we give it a name? The rotated version of OD is what? But still, I mean, this is orthogonal. This is meant to be orthogonal. So this is x. You say OD. OD is the scaled version of y plus z. So this is x cross y plus z. This is x cross y plus z. And what? Guess what? This vector here is x cross z. This is x cross z because you can, the point here, let's just label all the rotated version as, say, this is y prime, y1. So this is y1, big y1, big y1, and big z1. Okay, and here you have E1 and D1. So this pretty much finishes the proof. Let's just finish writing everything. Similar triangle. So it goes on. Now this is a geometric interpretation of the distributivity of the cross product. Okay, so what is this is x cross y, and similarly by the construction and so similarly x cross y x cross y plus z is OD1, is a vector OD1, where OD1 is obtained by rotating OD with respect to x counterclockwise, where OD1 is obtained by rotating OD with respect to or about x by 90 degree or half pi radian. Okay. So it just remains to show that. The difference between OD1 and OE1 is x cross z. Well, how do we show this is x cross z? Well, as we said, x cross z is what? X cross z. First we have ED, right? ED is that's the length of x cross e. We just need to verify that the direction also matches. Like x cross z should be perpendicular to both z and x. Hold on a second, is that true? Now, of course, this is perpendicular to x. Is that perpendicular to z, though? Is that perpendicular to z? Yeah, here, if you just take a bird-eyed view of this, top-down view, okay? Top-down view of this plane, I think it should be clear. So because of the rotation by 90 degree, so this is the triangle situation, ODE, top-down view. DE and YZ. Hold on a second. It said y plus z is in the plane. This is big Y, big Z. Okay, this is little. This is little z. This is y. Okay, and then rotate everything by 90 degree. You get something like this. We just need that this side DE, we just need DE is perpendicular to ZY, which is true. But how do we justify that? Because I don't remember an awful lot of theorems from classical Euclidean geometry anymore, simply because it's been so long since I took it in high school. By the way, it's interesting that in high school, I didn't do extensive like Euclidean geometry proofs anyway. I was taught by a teacher of mine in private, because in Ontario, the high school geometry isn't part of the mandatory. Sorry, high school geometry proofs. Okay, high school geometry, Euclidean geometry proofs are not part of the standard high school geometry curriculum anymore. So it's just the way it is. But I have no comments. But it's just the way it is. Okay, so E1 D1 is of course parallel to Z1 D1 due to similar triangle. And do we have Z1? So I was trying to say that Z1 Y1 must perpendicular to ZY. It seems rather natural, right? It seems rather natural, but how do we justify that? Well, I guess you can use a vector sum argument. You can use a vector sum argument because um, since since we know um, since we know Z1 Y1 Z1 Y1 is actually, you know what? I think let's just work with, it doesn't really matter, but let me just change that to, because Z1 Y1 wasn't used in the previous argument. So let's just use E1, let me rewrite that, okay? Just write, let's use dot product. This way is easier because I can't remember like the synthetic version, like the Euclidean geometry a la Euclid theorem regarding this result. So let's just use dot product. It should be okay. So E1 D1 perpendicular to E1 D1 perpendicular to Z. I want to do that. I just wanted to do that. E1 D1 perpendicular to Z. Okay. Since we know what the E1 D1 is the vector E1 D1 is E1 to D1 is OD1 minus OE1. Okay, and OD1, as we argued, is x cross y plus z. I guess you have congruent, right? You have congruent. Yes, of course, this is a rotation, so you have congruence, SAS. But how do you see it? Because in the diagram, the line I wish to show orthogonal don't intersect. I mean, you can extend them, but I just don't want it to make the diagram even more complicated. Okay, I'm pretty sure there are multiple ways. Thank you very much. And OE1, I just really want to finish this proof. Okay. OE1 is OE1, hang on. OE1 is x cross y. Okay, here x cross y is OE1. OE1 x cross y. Which is awkward, I know, right? X cross y. X cross y. And we establish and we know these fact that E1 D1, because of congruence, has length of ED. And ED is x cross z. Oh, actually, no. So this is, I'm trying to say is, well, I still wanted to show that E1 D1 perpendicular to, I haven't got that part right yet. E1 D1 perpendicular to Z is because of what? E1 D1 remember OE1 dot product. Okay, let's say you just use dot product. OE1 dot with Y. Dot with Y is 0. And OD1 OD1 dot with OZ is Y plus Z. Dot with Y plus Z is 0. So there you go. So you subtract Y plus Z. DE being plus Y. E1 D1 dot with Z is, yeah, D1 D1 dot with Z is OD1 minus OE1. And Z is Y plus Z minus Y. Z can be written this way. And then you just expand the dot product because we already have the dot product earlier. You get OD1 times Y plus Z, that's a 0. OD1 dot Y plus Z, that's 0. Minus OD1 dot with Y minus OE1 Y dot with Y plus Z and minus OE1 dot with Y, which is another 0. So does this vanish? OD1 OD1 dot with Y. Okay, OD1 dot with Y is this angle here, uses this angle here. OE1, hang on a second, this might need a little bit of work. Plus, last should be plus 0, it doesn't really matter. But okay, here, OD1 we expand this. Okay, I want to show that this vanishes, right? To show dot product equals 0, I need to show this dot. Okay, OD1 is OD1 dot with Y. Can I label this angle theta? OD1 has length of, remember, OD1 is from this side. OD1 has length OD, which is, damn, lack of value by transformation is a major drawback. I know, right? So, I'm stuck here. OE1 dot with Y plus Z. OE1 is this, Y plus Z is this. Somehow they vanish. Okay, it's really silly, right? It just boils down to, if you rotate a triangle, an arbitrary triangle, by 90 degrees in the same plane, and the resulting sides remain orthogonal. Calculating dot product should work, I know, right? So you got OE1 dot with Y0. Just make sure I didn't make many. OD1 with Y plus Z0. I need to show this is 0. Okay, so let's say if I don't expand this right away, so if I just say I have OD1 minus OE1, okay, dot with Z, dot with Z, okay, simply dot Z, OD1 dot with Z minus OE1 dot with Z. What do we have here? Well, nothing can be said, but OD1 dot with Z can be written as OD1 dot with Y plus Z minus OD1 dot with Y. And then you subtract OE1 with Z. Is that how it works? Yeah, this is true. So the first term is 0. But this term we don't know. We only have OE1 dot Y with 0. But here we don't have OE1 dot Y. So let's create another term. OD1 dot Y minus OE1. I need a Y. So let's do Y plus Z minus Y. To see we're stuck here in the same damn thing. Oh my god, I was so stupid, man. Like, if we can accept this, then we're done. Because you have the length match, also orthogonality. So, and if you already have this, if you can accept this, then this means ED E1 D1 is the cross product. So everything is done. But right now I don't have a good strategy of showing perpendicular hand wave power. Okay. Damn it. That's a loose end, which is annoying, but what can we do? Okay. Just a high school problem. This is a high school problem, which my lack of training in high school geometry is giving me a hard time. Yeah, just right now, just a simple diagram. You can even erase the middle line segment. If a triangle, arbitrary triangle, is rotated by 90 degrees, how do you show the corresponding sides are all perpendicular? Okay, guys, I think I might need to move on from this point. Okay, don't worry, I will I'll complete this part of the node and upload it to the link. Okay, to upload to the link, and I'll place a comment. I think you can take only OZ, OY. All right, OZ, OY. Yeah, OZ, you see, Vernon is saying YZ is OZ minus OY. Right, and you got OZ1 dot with OZ1 dot with OZ is 0. OY1 dot with OY is 0. So how do you proceed? Well, what we need is what? We need yz dot y1z1 0. Right? We need that. So isn't that the same problem? So yz dot y1z1 is oz minus oy dot oz1. Actually, I have no idea. I might still be confused, but let's try. oz1. Okay. oz1 minus oy1. So expand oz dot with oz1 minus oz minus, dot. Okay, I'm getting a little bit tired, but let's continue. I hope we can finish at least Rodriguez's formula today. It's perhaps we don't have time for quaternions, but yeah, I'll modify the thumbnail, just a matrix formalism, vector matrix form. But quaternion, let's save it for. Actually, you know what? We can do a quaternion thing tomorrow. I didn't pay full attention, so I hope it's something you tried. No, actually, I didn't. So I think this should work. Because I introduced extra complication of similar triangle. If you just work with congruent triangle, then hopefully things are easier to spot. So you got these terms as 0. These are rotated terms. Hold on a second. Why do I got okay, this is not right. This is not right. OZ dot with OY1, okay, and OY dot with OZ1. Okay, so do they vanish? Do the middle two terms vanish? That's the thing. Let's take a look at the diagram. OZ dot with OY1. OZ is this. OY1 is this. This is OZ. I'm running into the same issue. OZ, OY1. You see? OY and OZ1. You might need to use the angle relation. Huh? So how do you express that? OZ has the length of, you see, OZ has the length of just y plus z. Actually, you know what? Let me redraw that. Dang it. No, they're not equal. That's the same. You see, look at the diagram. I was stuck at this point. You need to use some trig business. OZ dot with OY1. Look at the diagram. OZ is this. OY1 is this. Second dot product. OY is this. OZ1 is this. I think you need some trig shenanigans. So OZ dot OY1 is y plus z length, right, times OY1. OY1 has a length of y. Times what? Let's just label the angle between OZ and theta to OZ and OY to be theta. This way, the angle between OZ and OY1 is cosine of theta plus half pi. Theta plus half pi is the angle between OY1 and OZ. And then minus OY dot with OZ1. OY, once again, has a length of y. OZ1 has a length of y plus, now it vanished, now it works. About time, you see? And in the middle, what's the angle between OY and OZ1? That's cosine of half pi minus theta. And they cancel. See, OZ, the angle are related in this way. So the angle between OZ and OY1 is theta plus half pi. And the other angle is theta minus half pi. And they have opposite sign, opposite cosine values, so they cancel out. So this way we're done. Finally. Okay. So you need some trig shenanigans to make it work. All right. So we finally managed to prove that the distributive law works for cross product. Okay. Okay. I'm just gonna get some water real quick. I'll come back. Yeah. So these are preliminary works for working with the 3D rotations. You can already see a cross product is very much essential ingredient in 3D rotation. Okay, give me 1 minute. I'll be back. I'll just get a cup of water. All right, I'm back. Guys, I'm back. Okay, so now we have this these three properties. We can get a coordinate formula. For x cross y. That's why I personally like the Euclidean style axiomatic that has transformation in its axiom. I have no idea. I just figured, you know, high school geometry is such a you know, like arbitrary combination of classical Euclidean and coordinate geometry mixed up together. So I don't even know what axiom is actually used. Okay, maybe this needs to be revisited at some point. Okay, but so far this proof works, so I'm very glad about that. Let's figure out a coordinate formula for x cross y. Still, let's do the basis expansion business. And for that, let's just going to use the summation notation. Sum over I from 1 to 3, xi ei. Okay, cross with the sum of yi ei, ej. Let's use ej. J from 1 to 3. My God, it's been raining heavily today, so you guys might even hear the sound of rain outside. All right, so yeah, just use bilinearity. First of all, it is still bilinear, and you get the sum of I and j. I'll just ignore the limits because it should be obvious. Xi times yj, ei cross ej. across Ej. So we need these components. Okay, so let's take a look at the diagram and make a table. E1, E2, E3, cross product. Make a table. See what's going on. First of all the diagonals are 0 by antisymmetry. And because of antisymmetry, we only need to figure out 3 values. And the rest we get for free. Let's figure out E1 cross E2. E1 cross E2 is E3. Use the right-hand rule. And E1 cross E3 is minus E2 from the diagram. And E2 cross E3 is E1. And then by antisymmetry, you get minus E3 here, plus E2 here, and minus E2 here. So as a result, every term in this double sum is now determined. So let's spell this. So let's spell things out. You get cat. So get x cross y equals here you got x1. Just read the index x1 y2 times e3. X1 e2 times e3 minus x1 y3 e2, okay, and then plus x1 y2 actually should be minus x1 y2 e3, and lastly plus x2 y2 e1. Okay, and then plus, and there you go, x3 y1. Hold on a second, did I make a mistake? Yeah, this is a mistake. Index should not be the same. If index are the same, then immediately get a 0. x2 y3 e1. That's a mistake. x3 y1 e2. Hold on a second. This is why, because I don't know how to check how many people are watching without opening my own stream, which is annoying, but probably a lot of people left because I stuck in the silly proof for so long. Anyway, that's okay. I'll just keep going on. And this is minus x3 y2 e1. Okay, so combining the terms, you get x2 y3 minus x3 y2 times e1 plus, I'm still here, thank you very much. Yeah, so I got stuck. So this is x3 529 fluctuation, nice. X3 y1 minus, because I really wanted to revisit all of this stuff, but I wasn't sure if it's justified to make that into a video. So I just, okay, I'm on vacation now, so might as well do some relatively easier math to relax. Okay, so this is y1 y2. I don't know how YouTube counts. It doesn't matter. It doesn't. If it's 0 people watching, I'll still do it the same way as I was saying a few past streams. All right, so you have this formula now, and of course the most familiar version you found in textbook is the determinant form. Determinant form, I mean, it's not literally a determinant, but it's just a way to memorize the formula. It's a mnemonic device. Mnemonic device, is that how you spell it? My goodness, I'm so illiterate. All right, so mnemonic device. How do you spell that? Yeah, mnemonic. My God, this is a weird word because you don't really see M and N together. Okay, this is not an actual determinant. So E1, E2, E3. P started with a P. Hang on.
Mnemonic.
Mnemonic. Mnemonic. The M is silent. Mnemonic. Okay, got it. Uh, thank you, Buckingham. So x1, x2, x3 are the first row. y1, y2, y3 is the third row. Okay, so and you can use it to verify what we did earlier was correct. So you formally expand it using the Laplace expansion. So you get E1 times the determinant of x2, x3, y2, y3. Yeah. So this matches x2, y3 minus x3, y2. And then you should use a minus E2 because of the determinant expansion business. So E2 here in the matrix is the entry 1, 2. 1 plus 2 is odd, so you put a minus sign. And get rid of this row and this column. You get x1, x3, y1, y3. Of course, expanding the determinant gives you x1, y3 minus x3, y1. And because of the minus sign, here you get x3, y1 minus x1, y3. So this is correct. And E3 is x1, x2, y1, y2. Okay, this is correct. So now you have the coordinate formula for the cross product. Okay, so that's a cross product. And quite often, we would run into the combination of more than one type of vector products in a single expression. You got products of three vectors in these two major forms. Product of three vectors. Okay, so there are two. One is x dot with y cross z. So this is called the scalar triple product. So you take the cross product first and then take the dot product. So this one is relatively easier. Scalar triple product, and you got also vector triple product, which is more complicated because it's a vector. Can you guys hear the cat? So the vector triple product is would look like x cross y cross z. All right. So let's take a look at them in particular. So first one has a nice geometric interpretation. The second one not so much, but there's a formula for that. The first one has a nice geometric interpretation because if you draw the diagram here, let's see here, for example, this is a plane determined by yz, assuming non-collinear, of course, as usual. So this is y and z. I can only hear you. I can only hear you. Okay, not a cat. Okay. Yeah, the cat was next to me and was asking for food. All right. So here, oh, actually here, yeah, this is x does not have to be perpendicular to the plane. Now it's general 3 vectors. So this is x. Okay. So here the plane is the span of y and z. Okay. Just a quick remark. Okay. I'm not sure if that's experience of you guys. Okay. Just a quick remark of we just did. I figured a lot of linear algebra text would start from, say, the definition of cross product using the coordinate formula. Using the coordinate formula and simply verify these properties algebraically. Say the antisymmetry law, the distributive law. Which of course is really straightforward. It's just a computation. But I figured the geometric insight can sometimes be obscure that way. And of course, it does not answer the question, why do we care about this complicated looking formula? And the same business with the dot product. Right? So it's usually, the way things is usually presented in mathematics textbooks, okay, not physics textbook, is you're given the coordinate formula as what's given, So the vectors are defined, okay, the vectors are defined as n tuples, in this case 3 tuples, triples of real numbers, and then you define the dot product this way and you verify the bunch of properties. And finally, eventually, if you give it a geometric interpretation of what you just did, which is also okay, but it feels to me that deriving everything from geometry and treat the vector treat the vector as a primary object and coordinates as a derived consequence is more revealing and more geometrically satisfying. I'm not sure if you guys feel that way, because this topic, 3D rotation, is highly geometric and of course also highly algebraic. I just wanted to emphasize the interplay between the two. All right, so here, what does the scalar triple product represent? Remember, the cross product of y and z is this vector, and magnitude equals the size or the area. The magnitude equals the area of the parallelogram spanned by y and z. So this is y cross z. And to take the dot product between y and y cross z, you just need to project x onto y cross z. So I agree with you. Most of the interesting properties of cross product derive from the fact it's orthogonal complement. Yeah, it's fundamentally geometric. Yeah. Of course, the most efficient presentation would be starting from the coordinate formula. And everything else can be verified just mechanically. You can let a machine do it. But I guess if you're learning this material, it's clear if you accompany with pictures every step of the way, as much as possible. All right. So thank you very much, Buckingham. So anyway, so I was saying that y plus z y cross z has the magnitude equals the area of, let me just use this notation, okay? The parallelogram spanned by y and z. Okay, that's what I mean. This is the area. And the scalar projection, just say, the scalar projection of x onto the direction of y cross z is the height. I just call it the height. This is h. So what is height times area? Of course, that's the volume. So that's the volume. Okay, so the triple scalar product, or scalar triple product, has a very nice geometric meaning. And of course, if you know a little bit about determinant, this is exactly the determinant with columns or rows. It's the same thing, x, y, z. Okay, it's the same. So here we have x dot with y cross z. So using the formula, you just get x1. I mean, I'm trying to keep things consistent with the determinant formula for the cross product. So this way, I'm just going to x1, x2. I'm putting the vectors as row vectors, but it really should be column vectors. It really should be column vectors because in linear algebra, x, y, z are all represented as column vectors. It's just the fact that transpose does not affect determinants that we can keep them as row vectors. Okay. So this is the volume. This is the volume of the parallelogram spanned by x, y, and z. Once again, this is not standard notation. Let me just write it in a very suggestive manner. Not standard notation, but I figure it's perhaps useful. Volume of the parallelogram how do you imagine latexing that? Okay. But x, y, and z. Use this curly bracket. And of course, it is clear that if the x, y, and z are linearly dependent, the triple product is 0. X dot y cross z equals 0 if x, y, and z are linearly dependent, meaning they are in the same plane. Okay. And so that's the definition. I mean, of course, you don't need to make a separate definition because you already defined cross and dot product. This is just a formula. This is a formula, and let's put one the formula, and second, there's a nice property. So, of course, since this has a meaning of the sign volume, in fact, this is the sign volume. Should probably write a sign volume. Determinant is sign volume. Unlike here, the length of the cross product is just area. That's just a strictly positive thing. All right. So I wanted to give the property that if you say change the order in the triple product, in certain situation it would remain constant. Okay. The idea is you want to keep the orientation the same. You want to keep the orientation of the bases x, y, and z. I'm assuming they are linearly independent. Okay. Assuming that they're linearly independent, because if not, it's just 0. It's uninteresting. Assuming x, y, and z are linearly independent, we wish to keep the orientation the same. So let's write let's draw a little diagram here. So let's say this is x, y, and z. The idea is if you make a cyclic permutation of the 3 vectors, the triple product remains the same. I mean, it should be clear from the property of determinants. If you, let's say, swap 2 rows, if you swap 2 rows, then the determinant pick up a negative sign. It's just the property of determinant. Okay. But if you perform a cyclic permutation, then the determinant should be the same. So that is to say, if you have x dot with y cross z, x, y, and z Okay. And if we make a cyclic permutation, let me just put the diagram here. Say now you have y. Okay, necessary to okay, so let's put it here. Y z to x and then come back to y. This is a cyclic permutation. So it's the same as y dot z cross x. Let's verify that using the formula. So y now occupies the first row, z occupies the second row, and x occupies the third row. So the first row is y. The original formula, the determinant is x is the first row, y is the second row, z is the last row. And let's say you wish to get to the configuration where y is the first row, z is the second row, and x is the last row. How do you get that? Well, let's first exchange y and x. If you turn that into y first, x second, and z last, a cyclic permutation is 2 transpose, easy peasy. Right, so here you do this, you exchange the first two rows, you pick up a minus sign. And then you do the exchange of y and x, x and z. You pick up another minus sign. This is the same now. So it does not change the value of the triple product. All right. So there's that. And then you can finally, there's another possibility of the cyclic permutation. Namely, if you put z first and then dot with x cross y, the value remains the same. So it's like the first circular diagram rotates this way, okay, and becomes the second. Okay, the top one takes the position outside of the dot, outside of the cross product, and the two vectors downstairs take the cross product. So this is a nice property of the scalar triple product. All right, so now let's move on to the vector triple product. The vector triple product, however, is a bit more complicated. So first, vector triple product. Now once again, let's still draw a diagram to illustrate the situation. So vector triple product here. X cross y, x cross y cross z quantity. So we want to visualize y cross z. This means we need a plane spanned by y and z. That's just natural at this point. All right. So let's say this is y and this is z. Okay, y cross z is of course orthogonal to the plane we just shown. This is the span of y and z. Okay, this is a y cross z. Okay, and x is an arbitrary vector. It does not need to satisfy any special property. So this is x. But as we can see already from this diagram, if you're taking the cross product between between x and y cross z quantity, the result should come back to the plane where y and z lives due to perpendicularity. Okay, so here let me just draw it this way. This is x cross y cross z. X cross y cross z. So there's that, and let's just label this angle here is use a perpendicular sign here. This is perpendicular, x and the cross product is perpendicular like so, and here you also have a little perpendicular sign. Y cross z also perpendicular to x, and these three vectors are in the same plane. So these are in the same plane. So that's what we're interested in. Our goal is to derive a formula for the vector triple product. Actually, it has a nice result. It has a nice result. Let me just write down the formula first, and then we will give it a proof. So here, the x cross y cross z is so it should be a linear combination of y and z. That's clear. It's because it's in the same plane as y and z. So what would be the coefficient? The coefficient turns out to be y times x dot with z and minus, okay, for the second coefficient, the coefficient of z is the minus of x dot y. So in many textbooks, x, y, and z are written in ABC. So this rule is called the back of the cab rule. Okay. In many texts, of course, it's just another, what's that? How's that? A new Buckingham what just told me another mnemonic device. In many textbooks, the formula reads this way: A cross B cross C quantity is B times A dot C minus C times A dot B. So they call it back cab rule, called so it might be easier to memorize it that way. For the back cab rule, okay? So, but let's just use our, actually, you know what? Let's use back cab just to perhaps easier to memorize. I'm just gonna switch things up. X is A now, Y is B now, Z is C now. Okay. Here you have span of B and C. All right, so it's already 4 hours, but I think I can finish up the proof for this vector identity, but that's okay. We're gonna continue. Okay, we're gonna continue tomorrow, same time. So in this video, in this live stream, we did the rotations for 2D, and we're on our way to get the formula for rotation in 3D. And right now we're just reviewing some basic vector algebra. Here, we have, this is A cross B cross C. The back of the back cab rule. Okay, let me just turn that into a different color. Another nice formula. And immediately, say if we have the cross product at the front. So here we have cross product at the back on the left hand side, right? But if we have, say, A cross B at the front, let me just write it this way. So immediately from this formula, you can get, say, use the just anti-symmetry. Okay, B cross C cross A. B cross C cross A is, so you just flip the sign on the right hand side to get C A dot B minus B A dot C. A dot C. So just use anti-symmetry, you get this. So put it into a nice formula. If you write A cross B and then cross C, so B is now A and C is now B. Use B substitute A here, C gets substituted B, so B here, and finally A is now C. Oh, actually this is messed up, sorry. Okay, so let me just set things up nicely. So it should be a dot product here minus dot product here. Okay, so B is now A here, yeah. And C is now B here, B here. And finally A is now C, so C here, C here. Okay, and you can perhaps put it even nicer. Actually, you can't put it even nicer. That's just the way it is. You see, it is, yeah. So remember, back cap rule applies when the second position, okay, the second position is the cross product, if that makes sense. If so, the bracket is applied to the last two of the three vectors. The bracket, when the bracket is applied to the last three vectors, you can apply the back cap rule. Otherwise, it doesn't work. Hold on a second. Did I miss something? Yeah, see here. Yeah, back cap rule is applied in this sense. And just to remind ourselves, this does not make sense. This is meaningless because cross product is not associative. Okay, let's just quickly check that. So, for example, E1 cross E2 cross E3 is what? Actually, that's a 0, huh? You know what? If maybe that doesn't work. So let's say E1 cross E2 cross E1. So E1 cross E2 is E3. E3 cross E1, look at the table. E3 cross E1 is E2. Yeah, look at the table. E3 cross E1 is E2. So what if we change the order? So E1 cross E2 cross E1. So E2 cross E1 here. E2 cross E1 is minus E3. And E1 cross E3, E1 cross E3 is minus E2. Do we get an E2 here? Oh, they're the same. Dang it. I need a counterexample. Yeah, just to make things easier. So you can put an E2 here. That solves the problem. Yeah, so that's a nice example because in the second example is obviously 0. E2 cross E2 is 0. So the second order is just 0. But the first one is not 0. That's enough. So if you cross E2 and E2 first, of course you get 0. In the first order, E1 cross E2 together and then cross E2, that's non-zero. That's already enough. Okay, so this is meaningless. You have to specify order since cross product is not associative. Probably another reason that people hate cross product, no? There's just so little property that it satisfies. This is not associative. Okay, so yeah, vector triple product, that's the formula, and now we wish to prove it. Okay, I've seen a bunch of proof of this identity before. There are purely coordinate proofs, which is straightforward. You just expand both sides and then declare them to be equal. But I like to do things a little bit more geometrically, but perhaps not fully geometric. Okay, so I wanted to show this identity with a combination of coordinates and just geometry, okay, and synthetic geometry. Perhaps that's easier to think about, but still keep some geometric intuition intact. So here, as we just mentioned, since A cross B cross C is perpendicular to B cross C, this means A cross B cross C is in the span of B and C, which means you just need to determine the expansion coefficients. So this is M times B plus N times C for some Mn in R. So there's that. So you want to just need to determine Mn. Okay. All right. So to find Mn, compared to our goal, so you want something. So you want to show that M is A times C, A dot C. You want to say to it remains to show. Let me just say it remains to show M is A dot C and N is A dot B. These are scalars. So how do we do that? Oops. Okay. Okay. So this might look a little like trickery, but here this is what I'm going to do. So define D to be B cross C, and E to be A cross D. Okay, I just want to mention that there's no trickery in this identity, at least not that I'm aware of. I'm pretty sure how it was discovered was just brute force expansion, and then people noticed certain patterns in the expansion. I just figured there is no trickery to it. Okay? You can, at this point, you can just use the coordinate formula, expand the left-hand side, and group terms into the form of the right-hand side. As simple as that. But I wanted to do things a little bit more geometrically. So at the cost of introducing some trickery. So we define these two vectors. So of course, E is now A cross B cross C. So basically, I'm just in the original goal, I'm just rewriting the left-hand side as A cross D, the left-hand side, which is the left-hand side. Okay, A cross B cross C. So now, why don't we figure out the coordinates of D? Well, D, using the formula, so D is, let's figure out, first of all, I want E1. I want E1. Want E1, the first coordinates of E. So E1, according to the formula above, according to the coordinate formula above, E1 should be E1. So E1 by the formula is A2D3 minus A3D2. So you just need D2 and D3. So once again, let's use the coordinate formula again. D2, by the coordinate formula, D2 is the second coordinate of B cross C. So this gives you B3 C1 minus C1 C3 B1. B1 C3. Okay. And what's D3? Well, D3 is B cross C, taking the third component. Once again, just use the coordinate formula for the cross product, and that gives you B1 C2 minus B2 C1. Right? Okay. And you now just substitute. So there's really not much to it. So E1 is what? E1 is A2 D3, so it's B1 C2 minus B2 C1. And just notice if there's any pattern in the formula. And then minus A3 D2. So D2 is B3 C1 minus B1 C3. All right. So expand, and you get something like this. And you get, hold on a second, this is, let's write it as B1, this is B1 A2 C2, okay, B1 A2 C2, and in the second expansion, if you take out B1, you get A3 C3 together, okay, and then the minus sign of, you might wonder why on earth am I doing this? Because I want the coordinates of B and C, see? Because I want the right-hand side to have the form of constant times B and constant times C. So I deliberately picked out B1 for that purpose. So here, because I'm talking about E1, I want a B1. And for the same reason, I need a C1 here. So let's factor that. So C1 times gets multiplied by the constant, just A2, B2, and then plus A3, B3. So you see, this is already very suggestive. This looks like a dot product, but there's terms missing. So we can add A1, C1. A2 C2 plus A3 C3. This way you get a dot product. And here we do the same shenanigan for the second term, C1 plus at A1 B1. And as if by miracle, the two added terms cancel out each other. So you see, here we added A1 C1. And here we added A1 B1. So the product is still A1 B1 C1, so they cancel out. So that's quite nice. So therefore this is just B1 A dot C minus C1 A dot B. Okay, so as a result, E1 is B1 times the constant A dot C. This has nothing to do with indices anymore, so that's nice. C1 A dot B. And similarly, you can show the rest. Similarly, E2 is B2 A dot C minus C2 A dot B. And E3 is B3 A dot C minus C3 A dot B. And therefore we're done. Okay, so the left hand side is B times A dot C minus C times A dot B. So that's the back cap rule now shown, vector triple product. All right, so yeah, because I'm getting very tired, I think this finish up the review of vector algebra in R3. Okay, so just to quickly summarize what we did today, we started with 2D rotation. The two formalisms for that. First is the matrix formalism, the 2D rotation matrix. The 2D rotation matrix turns out to be an orthogonal matrix. And this will play a role in the 3D case as well. Just didn't have time to get to. You also have the complex number formalism, which is, in my opinion, very beautiful. The complex number formalism as well as the Euler's formula. In particular, the Euler's formula to describe 2D rotation. And applying those results, in particular the 2D rotation matrix, you can get the 3D rotation matrix for rotations about coordinate axes. And in particular, be very careful about the orientation when you apply that formula. Okay, there was a mistake being made, now corrected, thanks to, I think the guy's name is Takion, who mentioned this mistake. So once again, thank you. And we also mentioned the formalism of Euler's angle, although we didn't pursue it much, because we still wanted to get to the matrix part. The Rodriguez formula was, we didn't have that. Okay, but you know what? Let's just give the formula. We'll continue that on the derivation tomorrow. If you get to the 6 degrees of freedom, how do you get to explain it? Well, 6 degrees of freedom is 3 degrees of freedom of translational degrees of freedom and 3 degrees of freedom of rotational degrees of freedom. If you think about it, the center of mass, or just any point for that matter in a rigid body, requires 3 degrees of freedom, x, y, and z. And the rotation is described by 3 degrees of freedom as well. So basically any rigid motion, like if you watched last Sunday's stream, this Sunday's stream of mathematical statistics and ballistic, where we derived the result that any rigid motion is a composition of a translation and a rotation. Right? So the translation needs 3 degrees of freedom, because to specify a translation, you just need a displacement vector. The displacement of the center of mass, right? Most commonly used in classical mechanics. And you need 3 degrees of freedom to describe the rotation. Right? So you clearly see the Euler's angle has 3 degrees of freedom. And here in the Rodriguez rotation formula, which I'm about to write down in a second, also has 3 degrees of freedom. The angle theta is a degrees of freedom. The orientation n only has 2 degrees of freedom because n is a unit vector, so it has a constraint. 3 degrees of freedom. The thing is, rotation SO3, by the way, this operator R and theta lives in the space SO3, lives in the group SO3. It is not it is difficult to embed it in some Euclidean space. It's difficult to embed SO3 in some ambient Euclidean space, and in fact that's unnecessary, and it introduces external information. So Hamilton originally thought, well, the rotation also needs 3 degrees of freedom, and because complex number can define can describe 2D rotation, can encode 2D rotation. Perhaps rotation can be encoded by a 3D vector. And he struggled that for over 10 years. Euler's explained they're greater or equal to, but is three-dimensional manifold? Well, to describe this as a three-dimensional manifold, well, you need if you want a formal proof, so let's just say, I gave the, because we didn't, we haven't even defined what's SO3, right? We haven't even defined what's SO3. So here, Vernon, we're about to show, okay, well, this is the plan. Okay, we're going to show that the Rodriguez formula defines an orthogonal matrix. R and theta is an orthogonal matrix, and its determinant is 1. So this raises the opposite question. Does every orthogonal matrix with determinant 1 defines a rotation? The answer is positive. This is something we also proved in the last stream. So basically, if you have a matrix in SO3, you can find its axes. Right? So that's the eigenspace associated with eigenvalue 1. You can always do that. And you can calculate the angle theta as well. So the opposite question is also true. So given an orthogonal matrix R, 3 by 3 orthogonal matrix R with determinant 1, you can always rewrite it in terms of a Rodriguez formula. So SO3 completely characterizes, is the false, okay, SO3 is the false possibility of rotation. SO3 is a possibility of rotation, and we want to show that SO3 is a three-dimensional manifold. Well, to do that formally, well, of course, you need manifold theory. You probably do that by giving it an atlas. Right? You give SO3 an atlas, and to do that, by definition, of course, you need to give that an atlas. So in an atlas, you have so-called charts, which are diffeomorphisms from an open subset in R3 to SO3. Right? You can certainly do that, but informally, let's think about why SO3 is three-dimensional. Okay, informally, why is three-dimensional? So imagine you have R in SO3. You need R transpose R equals I. So how many equations are there? There's 9 equations, right? Actually, it's 3. Is that 3 or 9? That's 9 equation. Hold on a second. How many genuine degrees of freedom are there? Because I transpose R, R transpose R is symmetric. This is a symmetric matrix. Yeah, so you don't need, so 9 equations are redundancy. You just need 6 equations. 6 equations is enough. Remember, this is a symmetric matrix, so you just need these entries to have, okay, R transpose R look like this. You just need to, yeah, have these constraints. So R in total has 9 numbers, and you have 6 constraints. It's 3-dimensional. If that makes sense. So that's once again a very informal justification. To prove this is a 3-dimensional manifold, you need, well, manifold theory. Okay, all right. I'll probably look at Lee's smooth manifold, that book. Right. So that's 6 degrees of freedom, and of course we mentioned 6 degrees of freedom in our ballistic live stream. The most cutting edge models for in exterior ballistic right now is the 6DOF model. And 6DOF model was first raised before World War II, but it didn't have time to be useful at the time because it requires extensive testing and data collection. It really came into full use during the Cold War, and now it is the industry standard. 6DOF is the industry standard. For example, the M777 howitzer used in Ukraine, 155 millimeters. So these algorithms are crucial for modeling artillery rounds, the flight trajectories of artillery rounds. Anyway, so let me just gonna write down the Rodriguez formula, and we will end the stream today. Okay. A second. The Rodriguez formula is given as follows. X prime is x cosine of theta plus n cross x okay. The thing is, the way I write x is not very consistent. Okay, hopefully that doesn't raise confusion. So the second term, n cross x times sine of theta, and lastly you have u times, oh actually n times n dot x and then times 1 minus cosine theta. So this is the Rodriguez formula. And it's an easy exercise to convert this into a matrix form, which we'll mention next time. All right. Damn it. Yeah, that's a Rodriguez formula. All right. All right, so that's it for today. Thank you very much again for everyone who joined the stream. You've been awesome. And I'll post this in the link. Okay, and I'll see you guys next time. Tomorrow, same time.